Hello and welcome. In this section, I want to start to tackle two very important questions that we're going to be answering throughout this entire course. The two important questions are, what is Docker? And secondly, why do we use Docker? We're going to first tackle why we use Docker by going through a quick little demo right now. Now I'm going to show you a little flow diagram. This is a flow of probably a process you've gone through at least once in your life before. It's a flow of installing software on your personal computer. And I bet at least once for you, this is what has happened. Maybe you have downloaded some installer, you run that installer, and then inevitably at some point in time, you end up getting an error message during installation. So what do? Well, you probably troubleshoot the issue by looking on Google, you try to find a solution, you eventually solve that issue. You then rerun the installer, only to find, hey, ta-da, you have some other error appearing. And then you have to go through this entire troubleshooting process again. So this is, at its core, what Docker is trying to fix. Docker wants to make it really easy and really straightforward for you to install and run software on any given computer. Not just your computer, not just your personal laptop or your personal desktop, but on web servers as well, or any cloud-based computing platform. I want to give you a very quick demonstration of this flow right here in action, and then show you how quickly I can solve installing a problem, or installing a piece of software by making use of Docker. So I'm going to very quickly go through the flow of installing a piece of software called Redis. Redis is an in-memory data store. We're going to be using it quite a bit throughout this course. But for right now, I just want to give you a quick demo of how it can be a little bit challenging to get installed on your own computer. So I'm just going to go through the installation steps here very quickly. So this is the Redis homepage. This is the official download page. In theory, I could use the documentation here to install Redis on my local machine. I'm going to go down to the installation section. And it very proudly says, oh yeah, just run these 4 commands right here, and boom, that's pretty much it. You can then run Redis. So I'm going to grab the first command right here. I'm going to copy it, and then I'm going to run it inside my terminal. So I'll paste. There's the same exact command. I'm going to run it, and sure enough, yep, I get an error message. Now in this case, the error message is a little bit predictable. It's complaining about a program that is just not installed on my local machine. Now I could definitely go and troubleshoot this, install that program, and then try installing Redis again, but that's the whole point. You kind of get into this endless cycle of trying to do all this troubleshooting as you are installing and running software. So let me now show you how easy it is to run Redis if you are making use of Docker instead. I'm going to go back over to my command line, and I'm going to run one single command. I'll say docker run -it Redis, like so. I'll hit enter. And then after a very brief pause, almost instantaneously, I have an instance of Redis up and running on my computer. And that's pretty much it. That is Docker in a nutshell. That is how easy it is to run software when you're making use of Docker. So to answer the question very directly of why we use Docker, well, we make use of it because it makes life really easy for installing and running software without having to go through a whole bunch of setup or installation of dependencies. Now we're going to learn many more reasons throughout this course of why we use Docker, but I wanted to give you a very quick demo and show you how easy it can be to get up and running with some new piece of software when you are using Docker. Let's take a quick pause right here. We're going to come back to the next section and start trying to answer the question of what Docker is. So I'll see you in just a minute. In the last section, we tried to answer the question of why use Docker. And we eventually said that we use Docker because it makes it really easy to install and run new software on our computer. We're now going to try to answer the other big question here, which is, what is Docker? Well, this question is a lot more challenging to answer. Anytime you see someone refer to Docker in a blog post or an article or a forum or wherever it might be, they're kind of making reference to an entire ecosystem of different projects, tools, and pieces of software. So if someone says, oh yeah, I use Docker on my project, they might be referring to Docker Client or Docker Server. They might be referring to Docker Hub or Docker Compose. Again, these are all projects, tools, pieces of software that come together to form a platform or ecosystem around creating and running something called containers. And so your immediate question might be, okay, well, what's a container? That's a good question, and that's a question that we're going to be trying to answer throughout this entire course. Just a moment ago, when I ran that command at my terminal of docker run Redis, It went through a little series of actions behind the scenes, and we're going to examine that entire series of actions very closely over time. But for right now, let me give you two important pieces of terminology. When I ran that command, something called the Docker CLI reached out to something called the Docker Hub, and it downloaded a single file called an image. An image is a single file containing all the dependencies and all the configuration required to run a very specific program. For example, Redis, which is what the image that I just downloaded was supposed to run. This is a single file that gets stored on your hard drive. And at some point in time, you can use this image to create something called a container. A container is an instance of an image, and you can kind of think of it as being like a running program. We're going to go into great detail over time to learn exactly how a container works exactly. But for right now, all we really need to understand is that a container is a program with its own isolated set of hardware resources. So it kind of has its own little set or its own little space of memory. It has its own little space of networking technology and its own little space of hard drive space as well. Okay, so I didn't really answer the question here of what Docker is. But we did learn at least that a reference to Docker is really talking about a whole collection of different projects and tools. And we also picked up two important pieces of terminology, a Docker image and a container. Now, these images and containers are the absolute backbone of what you and I are going to be working with throughout the rest of this course. So let's take a quick pause right now. We're going to come back to the next section, and we're going to start talking a little bit more about how we work with images and containers. So quick break, and I'll see you in just a minute. In the last section, we tried to answer the question, what is Docker? But we didn't really get a great explanation. We said, okay, it's a reference to a bunch of products. We then started to talk about something called an image and something called a container. At this point, we need to install some more software onto our machine so that you and I can work directly with images and containers so that we can get a better idea of how they work. So here's what you and I are going to do. We're going to be installing a piece of software called Docker for Windows or Docker for Mac, depending upon your operating system. Inside of this program are two very important tools that we're going to be making use of throughout this course. The first tool that's inside this package is something called the Docker client. The Docker client, also known as the Docker CLI, is a program that you and I are going to interact with quite a bit from our terminal. We're going to enter in commands to our terminal, issue them to Docker client. It's going to take our commands and figure out what to do with them. Now, the Docker client itself doesn't actually do anything with containers or images. Instead, the Docker client is really just a tool or a portal of sorts to help us interact with another piece of software that is included in this Docker for Windows or Mac package called the Docker server. This is also frequently called the Docker daemon. This program right here is the actual tool or the actual piece of software that is responsible for creating containers, images, maintaining containers, uploading images, and doing just about everything you can possibly imagine around the world of Docker. So it's the Docker client that you and I issue commands to. It's a thing that we interact with. And behind the scenes, this client is interacting with the Docker server. You and I are never going to really reach directly out to this Docker server. It's something that's just kind of running behind the scenes. So again, we're going to take a quick break right now. We're going to come back to the next section, and we're going to start installing this package so that we can get a better sense of how to work with images and containers. So quick break, and I'll see you in just a minute. In the last section, we downloaded and installed Docker for Windows or Docker for Mac on your personal computer. You should now be able to run the command docker version at the command line and see a little bit of text like this appear. I now want to write out our very first kind of meaningful command with the Docker client or the Docker CLI. We're going to run a very quick command here, and then we're going to go through a very specific flow of actions that occurred when that command got executed. So here's the command. We're going to write docker run hello-world. Yes, it is kind of a hello world thing of sorts. Don't worry, it's going to be rather interesting. I'll then press enter, and we're going to very quickly see a lot of text start to scroll along the screen. Now I'm going to scroll up a little bit, and you'll see a little hello from Docker message right here. And then you'll notice underneath that, it lists out the series of steps that just occurred when you ran that command. Now we're going to go over this series of steps right here in great detail, so if you want to, you can kind of ignore that text for right now. I'm going to scroll up a little bit further, and I want you to see up here, it says unable to find image hello world locally. All right, so with that in mind, let's go take a look at a couple of diagrams that are going to help explain what just occurred when we ran that command. All right, here we go. So at the terminal, you and I executed the command Docker run hello world. That starts up the Docker client or the Docker CLI. Again, the Docker CLI is in charge of taking commands from you, kind of doing a little bit of processing on them, and then communicating the commands over to something called the Docker server. And it's that Docker server that is really in charge of the heavy lifting. When we ran the command docker run hello world, that meant that we wanted to start up a new container using the image with the name of hello world. The hello world image has a tiny little program inside of it, whose sole purpose, sole job, is to print out the message that you see right here. That's the only purpose of that image. Now, when we ran that command and it was issued over to the Docker server, a series of actions very quickly occurred in the background. The Docker server saw that we were trying to start up a new container using an image called hello world. The first thing that the Docker server did was check to see if it already had a local copy, like a copy on your personal machine, of the hello world image or that hello world file. So the Docker server looked into something called the image cache. Now, because you and I just installed Docker on our personal computers, the image cache is currently empty. We have no images that have already been downloaded before. So because the image cache was empty, the Docker server decided to reach out to a free service called Docker Hub. The Docker Hub is a repository of free public images that you can freely download and run on your personal computer. So Docker server reached out to Docker Hub and said, hey, I'm looking for an image called hello world. Do you have one? Of course, the Docker Hub does. So Docker server downloaded this hello world file and stored it on your personal computer in this image cache, where it can now be reran at some point in the future very quickly without having to re-download it from the Docker Hub. So essentially, we downloaded it over here like so. After that, the Docker server then said, okay, great, I've got this image, and now it's time to use it to create an instance of a container. And remember what we just said about a container a moment ago. An container is an instance of an image. Its sole purpose is to run one very specific program. So the Docker server then essentially took that single file, loaded it up into memory, created a container out of it, and then ran a single program inside of it. And that single program's purpose was to print out the message that you see right here. So that's pretty much it. That's what happens when you run this docker run command. It reaches out to Docker Hub, it grabs the image, and then it creates a container out of that image. Now, one thing that you'll notice that's kind of interesting, if we run the docker run hello world command a second time, you'll notice that we are not going to see the message of downloading or container image not found locally that we saw the first time. So scroll back up to the very top. Here's the first time that we ran the command. You'll notice that up here it said unable to find image locally, but now the second time we did not see that message. And that is because we already downloaded it to our image cache on our personal computer. So the big lesson here is that the first time that you try to make use of any of these public images over here, you're going to have to do a little bit of a download, but then in the future after that, you can start up a container using that image much more quickly because the image has already been downloaded to your computer. All right. Now, in this entire flow, one thing that we've been kind of light on at this point is talking about exactly what a container is. So let's take a quick pause right here. We're going to come back in the next section and go into a little bit greater detail on exactly what a container is. So quick break, and I'll see you in just a minute. In the last section, we continued to talk a little bit about images, but we're still surprisingly light on some of the details around exactly what a container is. So in this section, I'm going to give you a behind-the-scenes look at what a container is and how it is created on your machine. Now, to understand a container, you first need to have a little bit of background on exactly how your operating system runs on your computer. So I'm going to first give you a quick overview of your operating system. Okay, so this is a quick overview of the operating system on your computer. Most operating systems have something called a kernel. This kernel is a running software process that governs access between all the programs that are running on your computer and all the physical hardware that is connected to your computer as well. So up here at the top of this diagram, we have different programs that your computer is running, such as Chrome or Terminal, Spotify, or Node.js. If you've ever made use of Node.js before and you've written a file to the hard drive, it's technically not Node.js that is speaking directly to the physical device. Instead, Node.js says to your kernel, hey, I want to write a file to the hard drive. The kernel then takes that information and eventually persists it to the hard disk. So the kernel is always kind of this intermediate layer that governs access between these programs and your actual hard drive. The other important thing to understand here is that these running programs interact with the kernel through things called system calls. These are essentially like function invocations. The kernel exposes different endpoints to say, hey, if you want to write a file to the hard drive, call this endpoint or this function right here. It takes some amount of information, and then that information will be eventually written to the hard disk or memory or whatever else is required. Now, thinking about this entire system right here, I want to pose a kind of hypothetical situation to you. I want you to imagine for just a second that you and I have two programs running on our computer. Maybe one of them is Chrome, like Chrome the web browser, and the other is Node.js, the JavaScript server-side runtime. I want you to imagine that we're in a crazy world where Chrome, in order to work properly, has to have Python version 2 installed, and Node.js has to have version 3 installed. However, on our hard disk, we only have access to Python version 2. And for whatever crazy reason, we are not allowed to have two identical installations of Python at the same time. So as it stands right now, Chrome would work properly because it has access to version 2, but Node.js would not because we do not have a version or a copy of Python version 3. Again, this is a completely make-believe situation. I just want you to kind of consider this for a second because this is kind of leading into what a container is. So how could we solve this issue? Well, one way to do it would be to make use of an operating system feature known as namespacing. With namespacing, we can look at all of the different hardware resources connected to our computer, and we can essentially segment out portions of those resources. So we could create a segment of our hard disk specifically dedicated to housing Python version 2. And we could make a second segment specifically dedicated to housing Python version 3. Then, to make sure that Chrome has access to this segment over here and Node.js has access to this segment over here, anytime that either of them issues a system call to read information off the hard drive, the kernel will look at that incoming system call and try to figure out which process it is coming from. So the kernel could say, okay, if Chrome is trying to read some information off the hard drive, I'm going to direct that call over to this little segment of the hard disk over here, the segment that has Python version 2. And Node.js, anytime that makes a system call to read the hard drive, the kernel can redirect that over to this segment for Python version 3. And so by making use of this kind of namespacing or segmenting feature, we can have the ability to make sure that Chrome and Node.js are able to work on the same machine. Now, again, in reality, neither of these actually need an installation of Python. This is just a quick example. So this entire process of kind of segmenting a hardware resource based on the process that is asking for it is known as namespacing. With namespacing, we are allowed to isolate resources per a process or a group of processes. And we're essentially saying that anytime this particular process asks for a resource, we're going to direct it to this one little specific area of the given piece of hardware. Now, namespacing is not only used for hardware, it can be also used for software elements as well. So for example, we can namespace a process to restrict the area of a hard drive that is available, or the network devices that are available, or the ability to talk to other processes, or the ability to see other processes. These are all things that we can use namespacing for to essentially limit the resources or kind of redirect requests for resource from a particular process. Very closely related to this idea of namespacing is another feature called control groups. A control group can be used to limit the amount of resources that a particular process can use. So namespacing is for saying, hey, this area of the hard drive is for this process. A control group can be used to limit the amount of memory that a process can use, the amount of CPU, the amount of hard drive input-output, and the amount of network bandwidth as well. So these two features put together can be used to really kind of isolate a single process and limit the amount of resources it can talk to and the amount of bandwidth, essentially, that it can make use of. Now, as you might imagine, this entire kind of little section right here, this entire vertical of a running process plus this little segment of a resource that it can talk to is what we refer to as a container. And so when people say, oh yeah, I have a Docker container, you really should not think of these as being like a physical construct that exists inside of your computer. Instead, a container is really a process or a set of processes that have a grouping of resources specifically assigned to it. And so this is a diagram that we're going to be looking at quite a bit anytime that we think about a container. We've got some running process that sends a system call to a kernel. The kernel is going to look at that incoming system call and direct it to a very specific portion of the hard drive, the RAM, CPU, or whatever else it might need. And a portion of each of these resources is made available to that singular process. Now, the last question you might have here is, okay, well, I get what a container is, but with that in mind, what is the real relation between one of those containers, or that kind of singular process and grouping of resources, to an image? How does that single file eventually create this container? Well, that's a good question. One more quick diagram. Anytime that we talk about an image, we're really talking about a file system snapshot. So this is essentially kind of like a copy-paste of a very specific set of directories or files. And so we might have an image that contains just Chrome and Python. An image will also contain a specific startup command. So here's what happens behind the scenes when we take an image and turn it into a container. First off, the kernel is going to isolate a little section of the hard drive and make it available to just this container. And so we can kind of imagine that after that little subset is created, the file snapshot inside the image is taken and placed into that little segment of the hard drive. And so now inside of this very specific grouping of resources, we've got a little section of the hard drive that has just Chrome and Python installed, and essentially nothing else. The startup command is then executed, which we can kind of imagine in this case is like startup Chrome, just run Chrome for me. And so Chrome is invoked, we create a new instance of that process, and that created process is then isolated to this set of resources inside the container. So that's pretty much it. That is the relationship between a container and an image, and it's how an image is eventually taken and turned into a running container. Now, there's still a tremendous amount more to learn about containers and images, so let's take a quick break and continue in the next section. In the last section, we had a long discussion about the relationship between a container and an image. We had said that a container is a running process along with a subset of physical resources on your computer that are allocated to that process specifically. We also spoke a little bit about the relationship between an image and a running container. Remember, an image is really kind of a snapshot of the file system along with a very specific startup command as well. Now, one thing that I want to mention very quickly here, in the last section, we spoke a little bit about the separation or the kind of the isolation of these resources through a technique called namespacing. And we also said that we could limit the amount of resources used by these control group things as well. Now, this feature of namespacing and control groups is not included by default with all operating systems, even though in the last section I had kind of specifically said like, oh yeah, your operating system has a kernel too. These features of namespacing and control groups are specific to the Linux operating system. So namespacing, control groups belong to Linux, not to Windows, not to Mac OS. So that might make you kind of question or wonder, how are you running Docker right now? You know, we are running a Docker client and we are running Docker containers on a Mac OS or a Windows operating system. How is that happening if these are Linux specific features? Well, here's what's happening behind the scenes. When you installed Docker for Windows or Docker for Mac just a moment ago in the last couple of sections, you installed a Linux virtual machine. So long as Docker up here is running, you technically have a Linux virtual machine running on your computer. Inside of this virtual machine is where all of these containers are going to be created. So inside the virtual machine, we have a Linux kernel, and that Linux kernel is going to be hosting running processes inside of containers. And it's that Linux kernel that's going to be in charge of limiting access or kind of constraining access or isolating access to different hardware resources on your computer. You can actually kind of see this Linux virtual machine in practice by opening up your terminal right now. And if you run that Docker version command again and look at your server, you'll notice that there's actually an OS entry on here. And you'll notice that it probably doesn't have your operating system listed. Mine, for example, right here says very specifically Linux as the operating system. So that is kind of specifying that I'm running a Linux virtual machine, and that's what's being used to host all these different containers that you and I are going to be working with. So just a little bit of interesting trivia. Now let's take another quick break right here. We're going to continue the next section and start digging into the Docker client a little bit more. So quick break, and I'll see you in just a minute. Starting this section and the next couple, we're going to start to look at the Docker client or Docker CLI inside of our terminal a little bit more and learn about some of the very basic commands that we use to interact with Docker containers and images. Now, fair warning here, some of these sections are going to be a little bit boring because we're essentially just going to be typing in commands and looking at the output that comes, but I'm going to do my best to make sure to share a lot of interesting information with you along the way. So let's get to it. The first command that we're going to look at is one that we ran very briefly before. It is the command that we're going to use to to create and run a container using an image. So at the command line, we're going to execute docker run and then the name of the image that we want to use as the basis for this container. Now we've already gone through this process once before. At the command line, we ran docker run hello-world. And then we saw that message appear on the screen. Now, using the knowledge that you now have about what a Docker container really is, I want you to think about what probably just occurred when we ran that command. Chances are that somewhere on our hard disk is an image that has that file system snapshot with one single program inside of it. Maybe that thing is called, I don't know, hello world. Who knows what it's really called? So when we executed docker run hello world, we took that little snapshot of the hard drive, we stuck it into this little container thing, or this kind of grouping of resources, and then we executed the command run hello world. And so the running process up here was hello world, that thing ran, and then eventually exited. So that's what is happening behind the scenes when you execute that command. Now there's a lot of variations on this docker run command and a lot of very small subtleties around it. So let's take a quick pause. We're going to come back to the next section. We're going to start looking at some of the interesting features around the run command. So I'll see you in just a minute. In this section, we're going to continue looking at the docker run command, or some slight variations of it. Now, before I show you the next kind of variation on this command that we're going to look at, I want to give you one quick reminder. Remember, anytime that we execute docker run with an image, we not only get that file system snapshot, but we also get this default command that is supposed to be executed after the container is created. So the variation on docker run that we're going to look at is going to give you a way to override this default startup command. Here's how we do it. We'll execute docker run the image name, just like we did before, and then after that, we'll supply an alternate command to be executed inside the container after it starts up. This is an override, so whatever default command is included inside of the image is not going to be executed. Let's try this out right now and just see how it works. All right, so I'm going to find my terminal, and I'm going to execute docker run, and then I'm going to specify my image. We're going to use a different image than what we used before. We're going to use an image called BusyBox, and I'll tell you why in just a moment. After that, we'll list out the alternate command to execute inside the container after it is created. And so I'm going to say that I want to run a command echo hi there. So this right here is the override. This is a command that will be executed inside that container. The echo command is going to print out hi there inside my terminal. So if this works the way we would expect, I'll see the text hi there appear. So I'm going to run that, and sure enough, yep, we see that. We can change the text provided here to the echo command as much as we please. So I could say, bye there, or I could say, how are you? You get the idea. Now I want to show you a small variation on that command, and this is going to start to make things a little bit more interesting than just kind of echoing text back over to you. I want you to run docker run busybox, and then the override command that we're going to use this time is going to be ls. If you've never used ls before, it's going to print out all the files and folders inside of a given directory. So let's try running this and seeing what happens. So according to our Docker container, when we print out our files and folders, we have bin, etc, dev, home, proc, root, sys, temp, user, and var. These are all folders right here. And if you are on, say, a Windows machine right here, these folders might look very strange to you and very unfamiliar. So in fact, these are folders that are being printed out that are not belonging to you on your computer. These are folders that exist solely inside that container. I want to remind you about exactly what happens when we create a container out of an image. So over here, we've got the BusyBox image. It has some default file system snapshot and some presumably default command. You know, who knows what it is off the top of my head, but it definitely has this default file system snapshot. The BusyBox image has default folders of bin, dev, etc, home, proc, root, and so on, all the ones that you see listed right here. So when we create a new container out of that image, we take this file system snapshot, we stick it in as the folder for that container, and then the command that we execute is ls. So we list out all the files and folders inside of our hard drive, which then prints out bin, dev, etc, home, proc, and root. So that's pretty much it. Now, one thing you might be a little bit curious about is why we chose to use the BusyBox image here as opposed to the Hello World one that we were using before. Well, let's go back over to our terminal really quickly, and we're going to try running Hello World with the ls command. So I'll do docker run hello-world, and I'll do ls right here. And you're going to very quickly see that we get a kind of nasty error message. Well, let's try doing the echo command and see what happens. I'll do docker run hello world echo hi there, and we get a very similar error message here as well. So what's going on? Well, here's the issue. When we run the alternate commands, or those alternate echo and ls commands with BusyBox, those commands work because ls and echo are two programs that exist inside of the BusyBox file system image. Somewhere inside of this folder system right here is a ls command, or an actual ls executable, and a echo executable as well. And so we can safely execute those commands with BusyBox because those are programs that exist inside this file system. However, with our Hello World program over here, the only thing that exists inside this file system snapshot is a single program, like one single file. And all that thing does is echo out or kind of print out that singular message that we saw when we ran that container. So these startup commands that we are executing are being based upon the file system included with the image. And if we try to execute a command inside the container that uses a program that doesn't or is not contained within this file system, we're going to see that error. Okay, so a little bit more on docker run command. Let's take another quick break right now and continue in the next section. In this section, we're going to take another look at a very commonly used command. So the command that we're going to look at is docker ps. This command will list all the different running containers that are currently on your machine. Let's try running it right now and just seeing what happens. I'll flip on over to my terminal and I'll run docker ps. When I run this command, you're going to see some headers for a table. At present, we have no containers running our machine, so we have no entries inside this table. At this point, we've only been running images or creating containers that run very quickly and then immediately close down. So for example, when we were running docker run BusyBox and echo hi there, that container starts up and then almost immediately exits us back to the command line. So if we want docker ps to be meaningful at all, we have to have some container that is running for some longer amount of time. In order to get a container running a little bit longer, we could substitute the command that is executed when that container starts up. So rather than running echo hi there, I'll try docker run BusyBox, and then I'll do ping google.com. This is a command that's going to attempt to ping Google servers and measure the amount of latency. It's a command that's going to continue running for quite a long time. So here it is running right here, and as you can see, it takes about 2 or 3 milliseconds for me to ping Google and get a response back. This command is going to continue running, so we can now run docker ps in a second window, and we should see this container up here in the listing. I'm going to open up a second terminal window, and then I'll execute docker ps. And when I do so, I'll then see that running container. I'm going to get this on one line really quickly. There we go. So this is a print up for the container that is currently running that was issued the command of ping google.com. We also see the container's ID, which we can use for a lot of other operations that we'll look into later on. We'll see the image that was used for the container. We can see how long ago it was created. We get a status. Currently, it's been up for 24 seconds. We'll see a listing of any ports that have been opened for outside access, and we're going to talk a lot about ports later on inside this course. And at the very end, we'll also see a randomly generated name to identify this container. In my case, the randomly generated name was Epic Corey. If I now flip back over to that running ping process, I can press Control-C on my keyboard to stop it. So I'll press Control-C right now, and I get kicked back to my command line. As you might expect, if I then run docker ps a second time, I would not see that container anymore. So docker ps specifically shows running containers. We can modify the docker ps command just a little bit to show all containers that have ever been created on our machine. To do so, we can execute docker ps -- all. Oh, just 2 dashes, there we go. When we execute that command, we'll see a listing of all the containers that we have ever created. And so I'm going to zoom out again here really quickly just so I can see this table. There we go. So for every one of these containers, these have all been containers that we have started up and then have either been shut down on our behalf or shut down naturally. So for each one of them, we'll see the container ID, image, command, when it was created, its current status, in this case they're all exited, any ports that have been opened up, again we'll talk about those later, and the randomly generated name for each one. So in practice, we're going to end up using the docker ps command quite a bit to see what containers are currently running on our machine. One of the most common uses of docker ps is not only to see what's running, but also to get the ID of a running container. Because like I said, we very frequently want to issue commands on a very specific container, and for that we need its ID. All right, so that's the docker ps command. Let's take a quick pause right here and continue in the next section. In the last section, we ran the docker ps command, and we saw one variation of it, which was docker ps -- all. When we ran -- all on here, we saw that we got a printup of all the containers we'd ever started up on our machine, which was kind of interesting, because it kind of begs the question, when does a container really get shut down? Why does it get shut down? And what happens when it gets shut down? So starting this section, I want to start to show you a little bit around the life cycle of a container, which is going to give you a better idea of what's going on behind the scenes. Now, before first investigating or just jumping to the end, like figuring out what happens when a container gets shut down, I want to kind of go all the way to the start and really figure out what happens when a container is first created. Now, we've learned at this point that to start up a new container from an image, we use the docker run command. But when we looked at this diagram, remember we looked at this diagram like 2 or 3 sections ago, you'll notice that I had put some very particular terminology here. I said creating and running a container. Creating a container and actually starting it up are actually 2 separate processes. So there's actually 2 additional commands in addition to docker run that we can use to start up a new container. Docker run, running that at your command line, is identical to running 2 other commands together. First, docker create, and then docker start. As you might guess, the docker create commands is used to create a container out of an image, and then start is used to actually start an image. But at this point, you might be a little bit curious of, hey, what's the distinction between creating a container and actually starting a container? Let's look at a diagram that's going to help you understand the differences between the 2. So we've looked at a diagram like this several times before. Remember on our image over here, we've got that kind of file system snapshot of sorts, and we've also got a startup command. The process of creating a container is where we kind of take the file system in here and kind of prep it for use in this new container. When we create the container, we're just talking about kind of prepping or setting up this file system snapshot to be used to create the container. To actually start the container, that's when we actually execute this startup command that might start up the process of like hello world, or in the case of that BusyBox one that we used, the echo hi there, or whatever process is supposed to be executed inside the container. So again, creating a container is about the file system. Starting it is about actually executing the startup command. So with that in mind, let's try flipping over to our command line really quickly, and we're going to start to investigate the differences between creating a container and starting a container. Over at my command line, I'm going to first try running the docker create and start commands with the hello world image. So I will first do docker create hello-world. When I run that command, I get this long string of characters printed out. This is the ID of the container that was just created. I can now actually execute the hello world command inside of this container by running docker start, and then I'm going to add on a little argument here. I'm going to say -a. We'll talk about what that is in just a second. And then I'm going to paste the ID that was just emitted right here. So I'm going to paste in that really long series of characters. and then when I run this command, we'll see that familiar welcome message appear. So what happened here? Well, again, first off, we kind of prepped the container by getting that file system ready. Then after that, we actually executed the primary startup command in there with Docker start. Now, what was with the -a right there? Well, to show you what's going on with that, let's try running Docker start again, but without the -a. So I'm going to run Docker start, and then I'm going to again paste in, oops, I lost the thing. I got to do the create again very quickly. So there's my ID, and I'll do Docker start, but without the -a this time. So when I run Docker start, you'll notice that I just see the ID. The -a command is what's going to make Docker actually watch for output from the container and print it out to your terminal. So the -a specifically means, hey, kind of attach to the container, so to speak, and watch for output coming from it and print it out at my terminal. So when I put on Docker start -a, that means give me any output that is coming from that thing. And when I run that, boom, there it is. So you'll notice that's a very small difference between Docker run and Docker start. By default, Docker run is going to show you all the logs or all the information coming out of the container. By default, Docker start is the opposite. Docker start is not going to show you information coming out of the terminal. All right, so that's the differences between Docker run and Docker start and Docker create. Let's take a quick pause right here. We're going to come back to the next section, and we'll talk a little bit more about exactly what it meant when we saw with the Docker PS all that exited status. So quick break, and I'll see you in just a minute. In the last section, we started investigating the life cycle of a container by using the Docker create and Docker start commands. We're now going to start to investigate the status of some of those containers that we've already started up on our machine, but have closed down for some particular reason. So we can print those all out with Docker PS --all. You'll notice that I have just one container listed as exited now, whereas before I had like 30. The reason for that is that I ran a command between the last video and this one to kind of par down that list. And of course, I will show you that command in just a second as well. So at this point, the only stopped or exited container that I have on my machine is this one right here. Let's try creating and running and then stopping one more container just to make sure that we're kind of on level footing. So I'm going to execute Docker run busybox echo hi there. If I then do Docker PS --all again, and then zoom out so I can see this a little bit better, there we go. I'll see the ID of that container. I'll see the echo hi there, and I can definitely verify that its status is definitely exited right now. When a container is exited, we can still start it back up. So just because a container stopped doesn't mean that it's like dead or cannot be used again. We can very easily stop and then start containers again at some point in the future. To start a container back up, we can take its ID and then execute Docker start and paste that ID in. Remember that if we use Docker start without the -a flag, however, we won't see any output from it. And so it might be a little bit more useful to do Docker start -a and then the ID. And when I do that, you'll notice that it printed out hi there again, which is kind of interesting. Let's take a look at a diagram to really understand this entire series of commands that we just issued. All right, here we go. So we've got our busybox image, and at some point in time, we definitely ran Docker create or Docker run. That took our file system snapshot and essentially got a reference to it inside the container. We then provided that override command of echo hi there. So that was the primary running command inside the container. That command ran, it then completed, the container exited naturally. When we then ran the Docker start command a second time, what happened was the running process, or this primary command, was issued a second time inside the container. When you have a container that's already been created, we cannot replace that default command. As soon as you start it up with the default command, that's it. The default command is then in place. So we cannot do something like, say, Docker start -a, the ID, and then try to replace the default command. I can't do something like echo by there. So in theory, this would be us trying to replace the default command. Again, can't do that. And if we try to run it, it's going to misinterpret the command that we just issued. It's thinking that we're trying to start up multiple containers at the same time. So once we have started up a container and let it exit, we can start it back up again, which is going to reissue the default command that was used when the container was first created. All right, now it might seem like going over all this lifecycle stuff is kind of unimportant. It might seem like I'm going really far into the weeds with it, but trust me, having a solid understanding of the lifecycle of a container is going to be so incredibly useful later on when it really comes down to figuring out how to troubleshoot these things and debug a running container. So I think we got a better idea on the lifecycle of a container. So let's take another quick break and continue in the next section. In the last section, I'd mentioned that I'd cleared out all the stopped containers on my machine. And so I thought you might be curious on how I did that. If I run docker ps --all right now, I can see that I currently have 2 stopped containers. So these containers right now are essentially just taking up disk space on my computer. And so it might be to my advantage to try to entirely delete them and not just leave them in this stopped state. To delete all these containers, I can run docker system prune. I'll then be presented with a warning here. So just to be clear, this is not only going to delete stopped containers, it's also going to delete a couple of other items as well, most notably your build cache. The build cache is any image that you have fetched from Docker Hub. So after running docker prune, you will have to re-download images from Docker Hub, which is not a really big deal. Just be aware that you're going to have to wait a couple minutes the next time you start up a container. Not really a couple minutes, but a couple of seconds, really. So we can enter in yes, hit enter, and then it will tell us about the deleted containers, and it'll tell me also how much space has been reclaimed by deleting those resources. If I then do another docker ps --all, I'll see that I do not have any stopped containers whatsoever. I really recommend you keep the docker system prune command in mind, because anytime that you're kind of done working with Docker for a period of weeks or months, or if you decide you just don't want to work with Docker again at all, you will want to run this command to delete any containers that are still just kind of sitting around, eating up disk space. All right, let's take another quick break and we'll continue in the next section. We were just talking about the differences between starting and creating a container. Along the way, we ran the command docker create, and then something like busybox echo hi there. We then got this printout of the container ID that was created, and then we found that we could start up the container by running docker start and then pasting the ID in. However, there is a little catch to that. We found that in order to actually see information being printed out from the container, we had to add in that -a flag right there. So what would happen if you wanted to get all the output from the container without having to add in that -a flag? For example, let's imagine that running docker start like this was a really expensive process, and we started up a process inside there that would take many minutes to run. Chances are, if we forgot to add on the -a flag to see the output from that, we might be a little bit frustrated with ourselves, because then we would have to rerun docker start -a second time and wait another couple minutes. In order to get around that, we can make use of an additional command of docker logs and then the ID of the container that we want to get output from. The logs command can be used to look at a container and retrieve all the information that has been emitted from it. Let's try using that docker create, start, and then logs command again and seeing what happens. So I will do docker create busybox, and I will echo hi there. I'll then take that ID and run docker start and paste the ID. That starts up the container. It executes echo hi there inside of it, and then it immediately exits. And so now at this point, I want to go back to that stopped container and get all the logs that have been emitted inside of it. So to do so, I can run docker logs and then paste that ID in. And I'll see that when the container had been running, it had printed out the string hi there. One thing to be really clear about is that by running docker logs, I'm not rerunning or restarting the container in any way, shape, or form. I'm just getting a record of all the logs that have been emitted from that container. The docker logs command is something that we're going to be using quite a bit as we are trying to debug or set up new containers, because as you can see, it's a really good way to kind of inspect a container and see what's going on inside of it. All right, still a couple more commands to get through, so let's take another quick pause right here and continue in the next section. In all these commands we've been running with docker create and start, there's kind of one oddity that I want to show you really quickly. Let's do a container creation and then a start, and you'll see some kind of weird behavior. I'm going to run docker create busybox, and then we're going to set up that ping command again. So I'll say ping google.com. That's going to create the container. I can then copy the ID right here and do docker start and paste that ID. And you'll notice that I did not put in the -a. So I have not attached this container. When I run that command, I see the ID of the container echoed back to me. And then I can do a docker logs and paste that ID in. And I'll see that, yep, it is in fact running the ping command. And if I do the docker ps command, I can see, yep, that container is running and it's continuing to execute the ping command. Now there's just one kind of odd thing here. How do we actually stop this container? Remember, the ping command is going to essentially go on forever, and we have to actually send it a signal and tell it, hey, ping command, please stop, like you're all done. No need to reach out to Google anymore. So we need to figure out a way to stop this running container. In the past, we've just been hitting Control-C on our keyboard, or we've allowed the container to automatically stop itself, as was the case with the echo command. So in order to stop a container that seems to be running amok on its own, we can issue either the docker stop command or the docker kill command. Both these are going to stop the running container, but they look like they kind of do the same thing here, so what's the difference between them? Well, here's what happens behind the scenes. When you issue a docker stop command, a hardware signal is sent to the process, or the primary process inside that container. In the case of docker stop, we send a sig term message, which is short for terminate signal. It's a message that's going to be received by the process, telling it essentially to shut down on its own time. Sig term is used anytime that you want to stop a process inside of your container and shut the container down, and you want to give that process inside there a little bit of time to shut itself down and do a little bit of cleanup. A lot of different programming languages have the ability for you to listen for these signals inside of your code base. And as soon as you get that signal, you could attempt to do a little bit of cleanup, or maybe save some file or emit some message or something like that. On the other hand, the docker kill command issues a sig kill or kill signal to the primary running process inside the container. Sig kill essentially means you have to shut down right now, and you do not get to do any additional work. So ideally, we always stop a container with the docker stop command in order to give the running process inside of it a little bit of time to shut itself down. Otherwise, if it feels like the container has locked up and it's not responding to the docker stop command, then we could issue docker kill instead. Now, one kind of little oddity or interesting thing about docker stop, when you issue docker stop to a container, if the container does not automatically stop in 10 seconds, then Docker is going to automatically fall back to issuing the docker kill command. So essentially, docker stop is us being nice, but it has only got 10 seconds to actually shut down. So let's now try using these commands on that kind of runaway container that we have right now. So I'll again do docker ps, and I'll see that the ping google.com container is still running. So I'm going to take the ID right there, and I'll issue docker stop, and then I'll paste that ID in. And then we're going to wait. And notice how we're kind of waiting here? We're going to end up waiting just about 10 seconds. We're waiting 10 seconds because it turns out that the ping command does not properly respond to a sig term message. The ping command doesn't really have the ability to say, oh yeah, I understand you want me to shut down. The ping command is rather, I don't know, what's the term for it? The ping command wants to do its own thing and it just wants to run forever. And so after we waited those 10 seconds, eventually the kill signal was sent to it telling it, hey, ping, you're done, get out of here, shut yourself down. And so that's why we had to wait a couple of seconds. Let's now take that container ID again. We're going to start the container back up and try killing it this time with using docker kill. So I'll first start the container back up with docker start, and I'll paste the ID in. And then I'll issue a docker kill and paste the ID again. And then this time you're going to see that's it, instantly dead, no grace period, just get out of here. All right, so that's it. That's the two commands that we're going to use for closing down containers that are running. Remember, you can always get the ID of the container ahead of time with docker ps. You can copy the ID and then run either docker stop or docker kill. And in general, I do recommend you use Docker stop to give the processes inside there a chance to shut down. And if they don't shut down nicely, as we saw with the ping command, eventually Docker is going to fall back to issuing a kill on the container instead. All right, so that's pretty much it. Let's take another brief pause and continue in the next section. Much earlier in this course, like in the first 1 or 2 sections, you saw me start up a new copy of Redis on my computer by using Docker. As a reminder, Redis is an in-memory data store that's very commonly used with web applications. You saw me start up a Redis instance using Docker, and it seemed to be really easy and very straightforward. But I want to show you kind of an oddity around using Redis with Docker very quickly. I took the liberty of installing Redis on my local machine directly without Docker being involved whatsoever, because I want to show you the normal way in which we might interact with Redis. I'm going to first start up an instance of the Redis server by running Redis server. Now, again, I am able to run this command because I installed Redis on my local machine without Docker involved. Chances are you do not have Redis installed on your computer, so don't try to run this command because it's probably going to result in an error. Now, when I run that command, you're going to see that, yep, I get an instance of the Redis server running. It's in memory. It's ready to store data or do whatever I need it to do. One of the very common ways in which we can kind of poke into this thing or into this server and inspect the data that is inside of it is by using a second program called the Redis CLI. So on my computer, I've already got Redis server running. I'm going to now start up a second program called Redis CLI. And again, the entire purpose of this thing is to kind of reach into that server and poke around inside of it. So I'm going to open up a second terminal window and I'll run Redis CLI. And that gives me a little prompt right here that allows me to issue commands directly to the running Redis server. And so I can do something like store my number, or excuse me, not store, but set my number is 5, and then I can then retrieve that value, and it prints out 5. So this right here is the normal interaction that you would see with Redis CLI. Clearly, it's really nice to be able to run the Redis CLI and interact directly with information inside that running Redis server. All right, so now you're probably wondering, where am I going with this? Well, let's try starting up Redis using Docker, and then you're going to very quickly see some interesting behavior around Redis CLI. So let's give it a shot. I'm going to stop my running stuff, and then I'm going to start up an instance of Redis on my machine using Docker run Redis. Now it's going to start up just about instantly for me. For you, it might take a second or two as it has to download the image, but overall it should be pretty darn quick. When you start up Redis, you might see a couple of warnings. Those are totally fine. You can ignore them. Just make sure that the very last line that you see is something that says ready to accept connections. So as long as you see that, you're good to go. All right, so this right here, what we are running right here is the Redis server. So I now want to start up a copy of the Redis CLI and try to work with the information that is being handled inside of this server. As you saw just a moment ago, I was able to open up a second console window and run Redis CLI. So well, maybe for Docker being involved here, maybe we just have to run like Redis CLI here. Oh no, that clearly doesn't do anything. Maybe we need to start up a second terminal window and try running Redis CLI there. Let's try that. We'll open up a second window and then run Redis CLI. Now, chances are you're going to see a message that says something like command not recognized or command not found. I see something that says could not connect to Redis. So what's going on here? Well, let's look at a diagram. So just a second ago, we started up a new container that is running Redis server. Now, Redis is running only inside this container. So if I tried to run Redis CLI outside the container, I have no access to anything that's going on inside there. And so there is no Redis CLI command to run outside the container. If we want to start up this CLI, we need to somehow get into this container and execute a second command inside of it, like this. We need to start up a second program inside the container. So to figure out how to do so, let's take a quick break. We'll come back to the next section and figure out how we can execute a second command inside of a running container. So I'll see you in just a minute. In the last section, we started up a new copy of the Redis container image. Inside there, we have a running copy of the Redis server. And we now need to figure out how we can somehow start up the Redis CLI also inside of that container. To do so, we're going to be making use of another Docker command. So the Docker command we're going to use is docker exec. Exec is short for execute, and we use it to execute an additional command inside of a container. We're going to write docker exec. We'll then put down -it. This little argument right here allows us to type input directly into the container. We then provide the container ID and then the command that we want to execute inside of the container. So let's try doing this right now and seeing what happens. I'm going to first go back over to my terminal. I'm going to verify that my Redis container is still running. I can either look at it inside the running window. Alternatively, I could run docker ps and see, yep, I still have that Redis image still going. So then to start up a second program inside the container, I'll run docker exec. Oops, forgot one thing here. We got to get the container's ID. We'll do docker ps, and there's the ID right there. So I'll do docker exec -it. I'll paste in the ID, and then the command that I want to execute inside there is redis-cli. And when I do so, you'll see that I now get that a little bit more familiar looking command prompt here, and I can write out something like set my value 5 and get my value, and it retrieves 5. So by using the exec command, we were able to start up a second running program inside of our container. And the -it flag right here allowed us to enter in text on our keyboard and have it be sent into that running container. As a very quick exercise, let's try removing the IT flag there and seeing what happens. I'm going to exit this by hitting Control-C on my keyboard, and then I'll do docker exec again, but this time I'm going to leave off the IT flags. So I'll do docker exec, the ID, and then redis-cli. And you'll notice that this time around, I just got kicked directly back to my terminal. I got kicked directly back because redis-cli was started up, but we did not get the ability to enter in any text. So when redis-cli was started up, but it very quickly realized, hey, I don't have any possibility of getting any text input, it decided to just entirely close down and kick us back to our terminal. Now, this idea behind kind of adding on this IT flag and adding in text here is actually something that's rather important in the world of Docker. So let's take a quick pause right here, and we're going to come back in the next section and kind of expand upon what IT right here means. So I'll see you in just a minute. In the last section, we found that we were able to connect to redis-cli inside of our running Docker container, and notice how mine is still running over here on the second window, by adding on the -it flag. So when I did that, we saw, yep, we got this prompt here. We could enter stuff in. I could then press Control-C to exit back out. However, if I tried running this command without the IT flag, it appeared that I just got kicked directly back over to my terminal. So in this section, I want to give you a better idea of what this -it flag right here is really doing for us. The first thing you need to understand is a little bit more about how processes run inside of a Linux environment. As a quick reminder, when you are running Docker on your machine, every single container that you are running is running inside of a virtual machine running Linux. So these processes are really being executed inside of a Linux world, even if you're on Mac or Windows. All right, so with that in mind, in this diagram, we've got 3 different running processes, all inside, in theory, of a running container, or really inside of a Linux environment. Every process that we create in a Linux environment has 3 communication channels attached to it that we refer to as standard in, standard out, and standard error. These channels are used to communicate information either into the process or out of the process. Standard in, as you might guess, is used to communicate information into the process. So when you are at your terminal and you type stuff in, the stuff you type is being directed into a running standard in channel attached to, say, the redis-cli. The standard out channel that is attached to any given process is going to convey information that is coming from the process. So standard out might be redirected over to your running terminal, and that's going to end up as being stuff that is going to show up on the screen. Standard error is very similar, but it conveys information out of the process that is kind of like an error in nature. So if redis-cli has some error inside of it, that's going to be communicated to the outside world over the standard error channel. And very similar to standard out, that's going to be redirected to show up on the screen of your terminal. So how does that relate to the IT flag when we do the docker exec -it? Well, the IT right here is actually 2 separate little flags. In reality, it's a -I and a -T, like so. but by convention, we usually just kind of shorten it down to be simply IT, which is 100% equivalent to the two separate flags. The -i on here means when we execute this new command inside the container, we want to attach our terminal to the standard in channel of that new running process. So by adding on the -i flag, we are saying make sure that any stuff that I type gets directed to standard in of Redis CLI. The -t flag is what kind of makes all this text show up a little bit pretty. Now, in reality, it's doing a little bit more than that, but at the end of the day, the real effect that the -t flag is to make sure that all the text that you are entering in and that is coming out shows up in a nicely formatted manner on your screen. And again, it's doing a little bit more behind the scenes than that, but at the end of the day, that's kind of its effect. Let's try attaching or doing our Docker exec on the running container one more time and leaving off the -t flag and just seeing what happens. So I'll do a Docker PS to get my container's ID again. Then I'll do a Docker exec, and then we'll do only -i this time. I'll put the ID in, and then I'll do Redis CLI. And so now this time, you'll notice how I have my cursor over here. It appears that this thing is waiting for input, but I do not see that kind of nicely formatted indentation I saw before. And if I put in like set my value 5, before I had a little bit of autocomplete functionality, but this time that autocomplete is definitely not there. I can still run that command though, and I still see OK, and I can still do get my value, and I still see the value come out. But again, all this stuff is not nicely formatted. And so that's kind of the purpose, more or less, kind of simplifying things here just a little bit, of that -t flag. Okay, so that's pretty much it. That's the purpose of IT. It allows us to have stuff that we type into our terminal directed into that running process, and allows us to get information out back over to our terminal. So with that in mind, let's take a quick break right here and continue in the next section. In the last section, we learned about the importance of the -it flag. In this section, I want to tell you about one last use of the Docker exec command. And this use of it is probably going to be the most common that you're going to be making use of on your own personal projects. A very common thing that you're going to want to do when you are using Docker is to get shell access or terminal access to your running container. In other words, you are going to want to run commands inside of your container without having to rerun Docker exec, Docker exec, Docker exec again and again all day. So in this section, I'm going to show you how you can open up a shell or a terminal in the context of your running container. So here's what we're going to do. I'm going to flip back over to my terminal. I'm going to verify that I'm still running that Redis container. I'm going to open up a second terminal window. Inside of here, I'm going to run Docker PS and get my container ID. And then I'm going to run Docker exec -it. I'll put the container ID in, and then here's the magic. I'm going to put in sh. And we'll talk about what sh is in just a second. I'm going to run that command, and you'll see that I get the little pound over here. Once I'm in here, I can now start to type out typical commands that I would expect to be able to run in a Unix environment. So for example, I could change my directory to my home directory. I could list out the files and folders inside there. Nothing there right now. Let's try going back to the root directory of /. And then if I do an ls, I'll see all the root files and folders of the container. I could execute commands like echo hi there. I can export variables, environment variables like export b = 5, and then echo that. So essentially, when I make use of this Docker exec command with sh over here, I get full terminal access inside the context of the container, which is extremely powerful for debugging. I could even do things like, say, run the Docker CLI directly, or excuse me, not Docker CLI, but Redis CLI. And that starts up the Redis CLI. And then when I'm all done, I can hit Control-C, and it looks like nothing's happening. So quick shortcut here, if you ever are in a container and it feels like you can't hit Control-C to exit, you can always try hitting Command-D, or excuse me, Control-D to get out as well. All right, so let's talk about what just happened there. So we ran Docker exec, which we've seen several times before, and then we did sh. So what is sh? Well, sh is the name of a program. It's a program that is being executed inside of that container. sh is a command processor or a shell. It's something that allows us to type commands in and have them be executed inside that container. you are already making use of a program very much like SH on your own computer. Chances are, if you're on Mac OS, you are probably using something like Bash. If you're on Windows, you're probably using something like Git Bash or PowerShell. Me personally, I'm making use of Z Shell. These are all programs that allow you to type commands into your terminal and have them be executed. And so when we start up SH inside of our container, that's just another command shell that we can use to execute commands. Traditionally, a lot of the different containers that you're going to be working with are probably going to have the SH command, or the SH program already included. Some more complete versions of containers or images are going to also have the bash command processor as well. So in some cases, you can make use of bash directly. In vast majority, you're probably going to be able to run the shell inside there to start up a command prompt and type in some commands. Okay, so again, I think that you're probably going to be using Docker exec -it with sh as the command very, very often when you start doing your own Docker development. All right, so we've spoken a whole bunch around Docker CLI. Let's take one more break here. There's just one or two quick topics I want to talk about, and we'll start to move on to our next big topic. In the last section, we spoke about how we could open up a shell inside of a running container by using Docker exec -it and then passing in shell, or just simply sh, as the command that we want to execute. We've been talking about all this in the context of the exec command, which we can use to execute an additional command inside of a container. But if we wanted to, we could also run docker run, the original docker run command right here, along with that IT flag, and start up a shell immediately when a container first starts up. Now, of course, if we start up a shell right when the container first starts, that's going to displace or keep any other typical or default command from running. But sometimes it is quite useful to get an empty container with a shell inside of it and just being able to poke around and not have any other process running. So let's try that out right now at our command line. I'm going to flip back over to my terminal. I'm going to run docker run. I'm going to put on the IT so that we can attach to standard in on the process that we're about to start up. I will run the busybox image, and then the program, or the primary command that we're going to execute inside the container, will be sh. So this means start up a new container out of the busybox image, run the sh program, which is a shell, and attach to standard in of that program. So when I run this, I'll be presented with a command prompt. And just like we saw a moment ago, I can run the ls command, I can ping google.com, and hit Control-C to stop it. I can echo a message, whatever I want to do. Again, this is a command that you might be using somewhat frequently anytime that you want to poke around a container. The downside to using Docker run with IT and sh is that chances are you're not going to be running any other process. It's a little bit more common that you're going to want to start up your container with a primary process of like maybe your web server or whatever it might be, and then attach to it a running shell by using the docker exec command, wherever it is, right here. But I just wanted you to be aware of this alternate use of Docker run. All right, now one last thing I want to cover in the next section, so quick break and I'll see you in just a minute. In the last section, we learned how to start up a shell inside of a container the instant that it was started. By the way, if you have a little bit of trouble exiting from this by hitting Control-C, which is usually how we exit out of a container, remember you can either press Control-D on your keyboard or you can just type in exit like so, and it will kick you back out. Now in this section, there's one very small gotcha, maybe not even a gotcha, but just a very particular thing that I want to go over to make sure that it's really crystal clear on how containers behave. I want you to recall back to a little bit ago when we were initially talking about what a container is. Remember that we gave this example of where Chrome had needed a particular version of Python and Node.js needed its own version of Python. And we had said that through that namespacing feature, we can kind of imagine that our hard disk had two little segments carved out of it. And anytime Chrome tried to access that hard drive, it would get its own segment. Anytime Node.js tried to access the hard drive, it would get its own different segment. And so the thing that I want to make sure is really crystal clear is that between two containers, they do not automatically share their file system. We're going to do a quick demo inside of our terminal just to really confirm that that is the case. So I'm going to open up my terminal, and I'm going to start up a new instance of that busybox image, and I'm going to start up a shell inside there. So I'll do docker run -it busybox, shell. So now I can list my files and folders inside of here, and I see just these default folders. I'm now going to open up a second terminal window, and I'm going to start a second container with the same parameters. So second terminal window, and I'll do docker run -it busybox sh. Now I'm going to open up one more terminal window, so this is going to be a third one. And inside of here, I'll do docker ps. And I can verify that I have two separate containers, both running a shell. Now I'm going to go to the first terminal window, and inside of here, I'm going to create a new file with touch hi there, like so. That's going to create a new file called hi there. There it is right there. I can run ls, and I'll see the file appear right away. Now here's the fun part. We're going to go over to the second terminal window, and I'll do an ls over here as well. And of course, I am not going to see that file of hi there, because these two running containers have absolutely completely separate file systems, and there's no sharing of data between the two. Again, this is kind of a small thing, but I just wanted to make sure that it was very crystal clear. So in general, unless you and I specifically form up a connection between two containers, we really consider them to be more or less completely isolated from each other and totally separate. All right, so that's pretty much it on the basics of Docker. So we're going to take a quick pause right here. We're going to come back to the next section, and we're going to start moving on to the next big topic that we're going to cover. So I'll see you in just a minute. Throughout this course, we've been making use of images that have been created by other engineers. So, for example, we have used, say, the Hello World image, or Redis, or Busybox. These are all images that were created by other engineers. We downloaded them onto our local machine, and then created a container out of them. At this point, we're going to start to figure out how we can build our own custom images so that we can run our own applications inside of our own personalized containers. The process for making an image is somewhat straightforward. Like all things, you just have to learn a little bit of syntax. So here's what we're going to do to make our own image. We're going to create something called a Dockerfile. A Dockerfile is essentially a plain text file that is going to have a couple of lines of configuration placed inside of it. This configuration is going to define how our container behaves, or more specifically, what different programs it's going to contain and what it does when it starts up as a container. Once we create that Docker file, we'll then pass it off to the Docker client, which you will recall is the Docker CLI that we've been using at our terminal. In turn, the Docker client will provide the file to the Docker server. The Docker server is what is doing the heavy lifting for us. It's going to take the Docker file, look at all the lines of configuration that we have inside of it, and then build a usable image that can then be used to start up a new container. Now, the Dockerfile is where all the complexity is going to sit. And like I just said a moment ago, it's not really going to be the worst thing in the world. It's just about learning a couple of new commands. That's all. In fact, just about every Dockerfile that you and I are going to put together is almost always going to look the same. Inside of every Dockerfile, we're always going to specify a base image. And we'll talk about what that means in just a moment. It's going to be one of the first things we have to do. After that, we'll add in some additional configuration to run commands to add in some dependencies or some more software, some more programs that we need to successfully create and execute our container. And then finally, we will specify a startup command for the image. So anytime we take that image and create a container out of it, it will be the command that is executed to essentially boot up or start the container. It's the same command that we've been talking about around all of these images all along. Okay, so that's it. That's all we have to do to make our own image. Essentially, just revolves around writing a Docker file. So let's take a quick pause right here. We'll come back to the next section and get started working on our Docker file. In the last section, we spoke about how we make our own custom image. We create a Docker file, we feed it into the Docker server, and that's going to eventually build a usable image that we can use to start up our own custom containers. And inside that Docker file, we're going to specify a base image, run some commands, and then eventually specify a command to run when a container is created out of the image. So in this section, we're going to start working on our own custom Docker file. Let me first tell you about what we're going to be trying to build. So we are going to make a Docker file that is going to create an image that's going to run Redis server whenever it starts up. Now, throughout this course, we've already been making use of that Redis image to start up Redis on our local computer, but I want to show you how to build that thing from scratch, or somewhat from scratch, just to be precise. So this is going to be the purpose of our Docker file and the image that we're going to create out of it. So let's get started right now. I'm going to first begin by flipping over to my terminal, and I'm going to create a new working directory, or kind of a project directory of sorts. And I'm going to call it Redis image, like so. Now, you can put this folder anywhere you want on your machine. Doesn't matter, anywhere is good. I'll then change into that directory, and then I'm going to start up my code editor inside that folder. Now, quick note, I am making use of Visual Studio Code, and I have configured it so that I could run it from the command line. So that is why I am able to run code dot right here. If you have not gone through those same steps, you will not be able to run that command and start up your editor. Essentially, all you need to do right now is start up whatever code editor you like to use and open up that Redis image directory that we just created. Then inside of here, I'm going to make a new file called Dockerfile. And notice how it has a capital D and it has no extension. So there's no JS on here. There's no shell. There's nothing like that. It is simply called Dockerfile. So then inside of here, we're going to write out a couple of comments to guide us through the process of creating our custom image. And it's going to essentially follow this template of steps right here. So the first comment I'm going to put down, and notice how we create a comment by putting down the pound symbol. I'm going to say that I'm going to use an existing Docker image as a base. I'm then going to download and install a dependency. And then finally, I'm going to tell the image what to do when it starts as a container. All right. Now, I'll be honest with you, the way we're going to approach this Docker file, we're just going to write out all the code inside of here, all the configuration. We're going to use it to build our image, and then we're going to come back and talk about all the configuration that we've written inside of here. To be honest, it's a lot easier to understand the configuration that we're going to write after you've actually seen the process of creating an image. So a little bit of just blind copy pasting here. Okay, so just follow along, and we'll very quickly come back and talk about the exact lines of code that we're adding in. So the first thing I'm going to write down is from Alpine. Then in the next section, I'm going to add run apk add -- update Redis. And then finally, on the very bottom line here, I'm going to add cmd, a set of square brackets, a set of double quotes, and then inside there, I'll put Redis - server, like so. Now I'm going to save this file. I'm going to flip back over to my terminal. I'm going to make sure that I'm inside of that Redis - image directory, and I'm going to run the command, Docker build dot. Don't forget the little dot on there. Notice how there's a little period. So I'm going to run that, and then we're going to very quickly see a whole bunch of output start to stream along here, and then eventually I see a message that says successfully built, and then blah, blah, blah. Now we're going to copy this ID right here, and then run docker run, and then I'll paste that ID in and execute this. And then we're going to very quickly see all the kind of output here that we saw previously when we ran that the Redis image. And the last message I should see is ready to accept connections. Okay, so we just went through the process of creating the Docker file, using it to build an image, and we started that image up. But we haven't really said anything about what really happened there. I'm going to stop the running container by pressing Control-C. We're going to take a quick break, come back to the next section, and talk about exactly what we just did inside this file and at the terminal. So quick break, and I'll see you in just a minute. In the last section, we put together our very first Docker file, and then very quickly used it at the terminal to build a new image. However, we didn't really talk about what was going on inside of here. So in this section and the next, I want to do a deep dive on all the configuration that we added to the Docker file, and also what happened over at the terminal afterwards. So let's get to it. All right. So I took every line out of that Docker file except for the comments and put it into this diagram right here. So you see from Alpine, run, and command. You'll notice that every line of configuration that we put in there looked kind of similar to the others. Every line started off with a single word that we referred to as an instruction. This instruction is telling the Docker server to do some very specific preparation step on the image that we are trying to create. The instruction from is used to specify the Docker image that we want to use as a base. The run instruction is used to execute some command while we are preparing our custom image. And then the CMD or command instruction specifies what should be executed when our when our image is used to start up a brand new container. Every line of configuration that you are ever going to add to a Dockerfile is always going to start off with an instruction. Now, we just used the 3 most important instructions to know. There are quite a handful of other instructions out there. We're going to look at a handful of them throughout the rest of this course. But again, from, run, and CMD are the most important ones to know and understand. After each instruction, we then provided an argument to the instructioner that kind of customized how that instruction was executed. So as you might guess, by putting from Alpine, we are saying we want to use a base image of Alpine when preparing our image. And we'll talk more about exactly what that base image is doing for us in just a moment. On the next one, we said we want to run this command. This command was the argument that was provided to the instruction. And then for CMD down here at the bottom, well, I bet you can guess, yeah, that is the argument to CMD. All right, so that's what was going on with the overall structure of the Docker file. But that doesn't really explain a lot of the pieces or kind of like what the intent of each of these lines were outside of the comments that we added on there while we were writing the Docker file. So let's take a quick pause. We're going to come back to the next section, and we're going to start to look at the output that we got inside of our terminal and try to understand how each of those lines of configuration was interpreted by the Docker server and used to build our image. So quick break, and I'll see you in just a minute. In the last section, we broke down the contents of our Docker file and got an understanding of the overall contents or structure of it. We now know that there's a handful of instructions that we can use to customize how our image is built. These are 3 of the most important instructions to know, and we'll introduce a handful of other ones over time. In this section, I now want to kind of break down what was really occurring behind the scenes with each of these instructions. We're going to first begin by taking a look at a little analogy. So this is going to be an analogy to help you understand the structure or purpose of those lines of configuration inside that Docker file. So, quick analogy. I'm going to tell you writing a Docker file is a little bit just like being given a computer, so a brand new computer with no operating system on it, and being told to install Google Chrome on there. So I want you to imagine what you would do if I handed you a computer that has no operating system on it, and I told you you have to install Google Chrome on here. Well, here is probably what you would end up doing. The first thing you might do is try turning on that laptop or turning on that desktop. And when you turned it on, you would probably maybe see some boot up process, but then you would eventually be given a message that says something like, hey, sorry, no bootable drive or no operating system. I'm just an empty computer. I don't know what to do. So the first thing you would probably do is install an operating system. You need an operating system on that computer in order to go through all these sequential steps on here. If you want to download Google Chrome, you have to go and download it from somewhere by opening up your web browser. And you have to navigate to chrome.google.com. You have to download the installer and open a file explorer and then execute that installer. So those series of steps right there, those are all steps that are facilitated by the installation of that initial operating system. If you didn't have an operating system, there would be no default browser to start up. You would not have a file or folder explorer to start up, and you probably would not have any way to run an executable file. All of these steps are kind of preceded or dependent upon having an initial operating system. So then going through all those initial steps, eventually you would be able to execute the Chrome executable and start up that browser. So these steps right here, very similar to what we just did inside that Docker file. When we specified that base image of Alpine, that was a lot like installing an initial operating system. By default, when we create a container, when we create an image, we have an empty image. There's really nothing inside there, no infrastructure, no programs that we can use to navigate around a file or folder system. There's nothing we can use to download or install or configure dependencies. There's nothing in there. So the purpose of specifying a base image is to kind of give us an initial starting point or an initial set of programs that we can use to further customize our image. So that is the purpose of that first line, the from Alpine. We said that we wanted to use the Alpine Docker image as kind of an initial operating system or a starting point for the image that we are creating. Now, your very initial follow-up question might be, well, why did we use Alpine? What is Alpine? So that's a good question. Another brief aside. Why did we use Alpine as a base image? Well, back to you, I'm going to kind of pose a question. I'm going to say to you, why do you use Windows or Mac OS or Ubuntu or some other Linux distribution on your personal computer? The answer is that you use any particular operating system because it kind of suits your needs. Windows might have a program that you need to use your computer effectively. You might use Mac OS because it has a built-in terminal, and that's really nice for you. In other words, you use one of these default operating systems because it has a set of pre-installed programs that is useful to you and what you are trying to accomplish. So we just made use of Alpine as a base image, as kind of like an operating system of sorts, because it includes a default set of programs that are very useful for what you and I are trying to accomplish. We are trying to install and run Redis. And the Alpine base image has a set of programs inside of it that are very useful for installing and running Redis. The command that was, or the program that was most useful for you and I for installing and running Redis was found on the second line of the Dockerfile. We had said run apk add update Redis. This is not a Docker command right here. This line has nothing to do with Docker whatsoever. APK is a program called Apache Package something, I think. It is a package manager that comes pre-installed on the Alpine image. And we can use that package manager that is built into Alpine to automatically download and install Redis for us. So we made use of Alpine because it had this package manager program automatically included inside of it. And so it made it a very convenient thing to start with inside of our Docker file. All right, so I think we got a better idea of what's going on with this from line. And I think we've got kind of a reasonable idea of at least the right-hand side of this one, the actual like command or line of code that was executed. But we still need to have a better understanding of what run over here is doing, have a better understanding of what command is doing, and kind of put this entire equation together. So quick break, we're going to come back to the next section and do a little bit more of a deep dive. So I'll see you in just a minute. In this section, we're going to start to really get a better idea of what was really occurring on our terminal when we executed that Docker build command. We're going to walk through each of these steps and not really analyze the structure of each of them, but really analyze the effect that they had on the image that we were building. So to get started, I first want to talk a little bit about the output that we saw in our terminal when we executed the Docker build command. So first things first, why do we use Docker build? Well, this is a new command that we have not used before tied to the Docker CLI. Remember what we said a little bit ago, when we create our Docker file, we then feed it into the Docker client, which turns around and gives your file off to the Docker server. And that's what builds your usable image. So when we ran docker build dot, that was us giving our Docker file off to the Docker CLI. The build command is what we use to take a Docker file and generate an image out of it. The dot right here is specifying what is called the build context. The build context is essentially the set of files and folders that belong to our project. It's a set of files and folders that we want to kind of encapsulate or wrap in this container. And we'll see some better examples of exactly what the build context is used for later on throughout the course, as our Docker builds start to get a little bit more complex. After running that command, we then very quickly saw a whole bunch of outputs start to scroll on by. The first thing I want you to notice here is that for every line of configuration that we put into our Docker file, we got an additional step added to this flow. So I see step 1 of 3 corresponds to the first line of our Docker file. I see step 2 of 3 corresponding to the second line, and I bet you can guess the third one down here, step 3 of 3 corresponded to the third line of the Docker file. Now with the very first step where we said from Alpine, the first thing that occurred was the Docker server looked at our local build cache and it checked to see if it has ever downloaded an image called Alpine before. In our case, it probably hasn't. So the first thing that occurred was the Docker server reached out to the Docker Hub, which you would call is a repository of existing Docker images that are free for public use, and it downloaded that image, the image called Alpine. So pull complete means, yep, it was successfully downloaded, and well, it really tells you that very clearly right here. Downloaded newer image for Alpine latest. So that first step right there, kind of boring. We basically just downloaded an initial starting image to use as a base. Things started to get a little bit more interesting on step number 2 right here. So there's a couple of lines of code or output right here that I want you to really take a very good look at. You'll notice the first line right here says running in and then an ID. So that's very key right there. I want you to remember that for just a second. And then a little bit lower, you'll notice that it says removing intermediate container, and it printed out the exact same ID that we saw back up there. So it looks like this ID right here is the ID of a container. But what container? We'll dive into that in just a second when we look at a diagram that's going to kind of explain this flow. You'll notice that we also saw some very similar output down here for step 3 as well, where it said running in blah, blah, blah. And then very shortly after that, removing intermediate container. One last thing I want to point out here is that for step number 1 up here, you'll notice that there is no kind of like intermediate container printout. So it appears that for every instruction that we added to the Dockerfile, besides the first one, it appears that some like container of sorts was created. So with that in mind, let's flip over to a diagram and really walk through what just occurred. All right. Now, I know we're going through this stuff like really intense and in-depth, but honestly, getting a very fundamental or solid understanding of this Docker build process is really going to help you understand Docker in general. That's why we're going through so much detail. Okay, so in this diagram, we've got a container on the right-hand side, we've got the Alpine image on the bottom left, and then our series of 3 commands over here. So the first thing we did was specify from Alpine, and as we saw, that basically went out and downloaded the Alpine image off of Docker Hub. Remember that an image has a file system snapshot and some startup command. And at this point, we don't really know what the startup command for Alpine is, but we don't really care that much. The next line was the run apk add update Redis. So here's exactly what happened behind the scenes. When Docker server saw this line of configuration right here, it looked back at the last step that just occurred. So it looked back at this step, the from Alpine step. It looked at the image that came out of that previous step. The image that came out of the previous step was the Alpine image. Then on the run line right here, it took that image and created a new container out of it. So in memory, we very temporarily got a brand new container created at the very start of step number 2. And that's what this running in blah, blah, blah right here means. It means that it created a temporary container out of the image that was sourced during the previous step. So we can kind of imagine that we took the entire file system snapshot from the Alpine image and we stuffed it into this very temporary container that was created just for the second step right here, or the second instruction. After creating this temporary container, this command right here, the command that we just added on, was executed inside that container as its primary running process. So we took that run command, we took that line or that full command right there, and we executed it as a process inside of the container. So this is this container's primary running process. As we said in the last video, APK is a package manager that is built into the Alpine image. So this command executed inside the container, and while it executed, it went through the process of downloading Redis. That's what happened right here. It downloaded and installed Redis and a couple of dependencies for Redis. So we can imagine that during that installation process, we maybe got some like new folder on this container's hard drive right there. Maybe it was something called like simply Redis. Now, I want this to represent the Redis program. It didn't install it in the root directory or anything like that, but let's just imagine that apk add downloaded and installed Redis onto this container's little hard drive right here. So we now have a container that has a file system snapshot that contains the newly installed copy of Redis. Now look at what happened immediately after that. After that container, or excuse me, after that package was installed, we then stopped that container. We took a file system snapshot of that container, and then we stopped it entirely. So we're saying right here, that temporary container that was just created, we stop it, and we then take its current file system snapshot, and we save it as a temporary image with this ID right here. So the output of everything inside of step number 2 is a new image that contains just the changes that we made during this step. So we can now kind of imagine that this ID right here, this is the ID to a very temporary image. So I'm now going to update the image down here on the top left-hand side. And I'm going to say that is the 3.8 EC image. And inside that image, it now has a installed copy of Redis. And we also threw away that intermediate container. So that is the end result of step number 2. In total, we created a temporary container out of the Alpine image. We executed this command inside that container, and then we took that container's file system and saved it as a temporary image. So we now have this very temporary file system snapshot right here that has Redis included. Then we move on to step number 3, where we execute CMD right here. So I bet you can imagine what happens here. With CMD, we're going to look at the image that was generated during the previous step. So in this case, the image that was taken from the previous step is this 3.8 EC image. We create a new, very temporary container out of it. And when we make that container, we take the image's file system snapshot and stuff it into this container. And then with the CMD, this is setting the primary command or the primary process of the container. So the container does not actually execute Redis server. It doesn't execute this command. It just tells the container, hey, like, just so you know, if you were to ever run for real, you should be running Redis server as your primary command. So the container is told this is supposed to be your intermediate, or something, this is supposed to be your primary command, and then it shuts down that container and takes a snapshot of its file system and its primary command. So the end result is successfully built this ID right here. This is the final image that was created out of this entire series of steps. So in step number 3, at the very end, we remove the intermediate container. We take a snapshot of its file system and its primary command, and then we save it as an output, as an image with an ID of FC60. So here's the container, the very temporary one. We take a snapshot of its file system. So I'm going to put it over here. And we also take a snapshot of its running primary command, or excuse me, not running primary command, but primary command that should be executed when the container starts up in the future. And so we specify the startup command as Redis server, and then we save that entire thing as an image with the ID of FC60. And so the end result is this right here. The end result is our image with that ID that has our full file system snapshot with Redis installed and a startup command that has been specified. All right, so at long last, that is the full story. That is what happened with the Dockerfile. Now, the real takeaway that I want you to understand here is that basically along every step along the way, not basically every step, but really every step along the way, with every additional instruction, we essentially take the image that was generated during the previous step, we create a new container out of it, we execute a command in the container, or make a change to its file system. We then look at that container, we take a snapshot of its file system and save it as an output for the next instruction along the chain. And then when there is no more instructions to execute, the image that was generated during that last step is output from the entire process as the final image that we really care about. Whew. So that's a lot of information. So let's take a quick pause right here and we'll continue in the next section. In the last section, we went over the behind-the-scenes flow of what occurred during that Docker build process. Now, that was a rather long section, and we went through a lot of detail. So in this section, I want to do a quick recap, just a very quick overview on the really important critical flow to understand. Now, if you don't want to hear me lecture about this stuff anymore, if you feel like you already have a good understanding, no problem. Pause the video right now and move on to the next section. Again, we're only going to do a recap of what we just spoke about a moment ago. Okay, so here's the recap with a slightly different diagram. So everything started with the from Alpine instruction. That told the Docker server or Docker daemon to go and download the Alpine image. And we use the Alpine image as a base because it comes pre-installed with some really handy programs that are useful for us creating our image. The next thing that occurred was the run instruction was executed by the Docker server. The first thing that occurred there was it looked for the image from the previous step. And so it went back to the previous step and got the Alpine image that had just been downloaded. That image was then used to create a brand new, very temporary container. So here's our container over here. And then the command that we had specified, so apk add -- update Redis, was executed inside of that temporary container. The apk program was executed, it downloaded and installed Redis inside the file system of that container. So the result is a container with a modified file system. It now has Redis added onto it. We then took a snapshot of that container's new file system, and the result was a file system snapshot. We then shut down the temporary container, like this one right here that had just been created, and we got our image ready for the next instruction. And the image that we're using is that file system snapshot, the modified one that we just created when we installed Redis. So you can now imagine that we are now passing on to the next step. We are essentially passing along the Alpine image, but with Redis added on top. So we then move on to the command Redis server instruction. We again get the image from the previous step. We again create a temporary container out of it, but this time around, rather than executing a command inside there, which is the purpose of the run instruction, we instead use the cmd instruction, which is used to specify what the container should do, or excuse me, what the image should do when it is started up as a container. So we told the temporary container that we just created that whenever it gets started in the future, it should try to execute the command redis-server. And the result was a container that has a modified primary command. We then shut down that temporary container and we got it ready, or we took an image out of it and got it ready for the next instruction. But in that case, there are no more instructions, no more steps to execute inside this file. And so the output of the overall series of steps is whatever image was generated during the last instruction inside of our Docker file. All right, so like I said, just a quick recap on that entire process one more time, because it's not super critical that you have an in-depth understanding here, but it definitely makes a lot of this Docker stuff a lot easier if you have a good grasp on this entire flow. So let's take a quick pause right here and we'll continue in the next section. In this section, there's one last quick thing that I want to mention about the Docker build process. This is an important thing to understand because it's what gives Docker so much performance whenever creating a new image. All right, so I'm looking at my Dockerfile right here. We have our 3 instructions, and as you very well know by this point, out of each one of these instructions, we essentially get a new image. So from Alpine, we get the Alpine image. From the run instruction, we get a temporary image that gets fed into the cmd instruction, which gives us another temporary image. So at every instruction along the way, we have a file system snapshot and a startup command for that image. Now, I want to show you something a little bit interesting. I'm going to go back over to my Docker file, and on the run instruction, I'm going to add a new one right underneath it. I'm going to say run apk add -- update gcc. So we're just installing a very random second dependency here. There's nothing important that you need to know about GCC. We're just installing a second dependency. So I want you to think about what effect this is going to have on our overall flow. Essentially what it's going to do is add in a new instruction right here that's going to look a little something like this. We're going to see a new one. Let's see how quickly I can do this edit. We're going to get our new instruction right there. It's going to be very similar to the image from the previous step. And it's going to have a new little program or folder or something inside of it of GCC. So essentially it is identical to the previous image, but it has this extra little program that has been added in. Let's now flip over to our terminal. I want to rebuild our image, and you're going to notice something kind of interesting. So back over at my terminal, I'm still inside of my Redis image directory, and I'm going to build my image a second time by running docker build dot. All right, so we're going to very quickly see some installation steps right here as it adds in that additional package. But I want to scroll up to the second instruction, and I want to point out something interesting up there. So we still see step 1 of 4 right here where we do from Alpine. You'll notice that we do not see any of that like fetching image stuff that we saw the first time because we have already fetched the Alpine image. We've already downloaded it from the Docker Hub, and so we don't have to go and download it a second time. Now the interesting thing that I want to show you, and this is where Docker gets so much of its speed and performance from when building an image, you'll notice that during step number 2 right here, we do not see any of that stuff around running in blah, blah, blah. We don't see any fetch. We don't see any installation of dependencies. Instead, we see a single message that says using cache. So what this means is that Docker has realized that from the previous step to step number 2, nothing has changed from the last time that we ran Docker build. In other words, it knows without a doubt that it's going to get the same image from the previous step because it's the exact same instruction that it was before. And then for step number 2, Docker knows that it has already executed the command apk add update redis. It's already generated an image out of that step, this image right here. And this image has been cached and stored on your local machine. So rather than going through the process of creating another container out of the Alpine image and running apk add update redis inside that container a second time, it says, you know what, I've already done this work. I'm just going to use the image that I generated during the previous step again. But then after that, Docker correctly sees that there is a new command in play. And this is not add update redis, it's add update GCC. It sees that there's a new command right here, or a new instruction in play. And so from this point on, it decides, well, you know what? Something has changed during the build process. We probably can't use our cache anymore. And from here on out, we have to go through that process of generating a container and running a command inside the container and taking the snapshot and going through all that stuff again. Now, the interesting thing about this is that it has now executed run apk add GCC, and it has generated an image out of that instruction right there. So if we now run docker build dot a third time without making any changes to our Docker file, Docker is going to correctly see we have made no changes to the Docker file. None of these steps have changed whatsoever, and so it's going to use the cached or saved versions of each of these images in building this new one. Let's do that right now, and you're going to see it in action. So we're going to do docker build dot a third time, and you'll notice that build process went extremely quickly. So Docker correctly realized that it's already downloaded Alpine. It's realized that it already ran the run command on top of Alpine, so it's using the cached version of that image. It knows it's already done the GCC, so it's using the cached version of that, and it knows that it's already executed command redis server on top of the output of the GCC step, and so it's using the cache there again. So the lesson to learn here is that anytime that we make a change to our Docker file, we're going to have to only rerun the series of steps from the changed line on down. As a quick example of that, let's try taking this GCC line right here, and I'm going to cut it and put it right above Redis. So even though we're still taking the Alpine image and adding GCC to it and adding Redis to it, the series of steps have changed. And so Docker is going to say, okay, well, this time we're taking Alpine and first adding in GCC. So it will use the cached version of Alpine, but it's not going to have a cached version of the GCC add to use, because the last time that it ran that, it added GCC only after installing Redis. So essentially the order of operations is different, so the cache cannot be used. So I'm going to save this file after moving GCC around, and we'll try rebuilding our image for a fourth time. So I'll do docker build dot, I'll run that, and now you're going to see, yep, it has to go through that installation process all over again because the order of operations have changed. However, it only needs to rerun the steps from the changed line on down. And so we have to rerun the entire add GCC, we rerun the entire add Redis, and we have to rerun the command Redis server. All right, so again, if you are not changing your Docker file, that's great because it means that we can use cached versions for building the image. But the real lesson to learn here is that if you ever expect to have to change your Docker file, you always want to put those changes like as far down as possible. Now, for right now, that might sound really confusing, but we're going to very quickly go through another example in a couple of videos where you'll see that by changing the order of operations inside of our Docker file can dramatically change how long it takes to rebuild our image. All right, so quick pause right here, and I'll catch you in the next section. At this point, we have the ability to create a new custom image out of our Docker file, and we can do so by running docker build dot. The output from all that is this very last line right here that says successfully built blah blah blah. This is the ID of the image that was just created. So we can now create a container out of this image by copying the ID and running docker run and then placing the ID in there. Now when we run this command, an instance of our image will be created. We'll get a new container, and inside that we're going to be running an instance of Redis server. So I'll hit enter, and there we go. We've got our copy of Redis. And again, all the warnings you can totally ignore. Now, one thing I want to point out here is that having to execute docker run and then paste in that ID, well, I don't have it anymore, but having to paste in that ID is kind of a pain. And it sure was a lot nicer earlier in the course when we were able to do stuff like just simply docker run Redis or docker run hello world. In those cases, we didn't have to memorize an ID to use. So we can actually do the same by slightly changing the form of the docker build command. Here's what we're going to do. We are going to run docker build, and then we're going to add on this little argument right here that is going to tag the image that is created and make it a lot easier to refer to it by a name that you and I can customize. The convention for this is your Docker ID, a slash, the name of the project that you're working on, a colon, and then the version, which traditionally is going to be latest whenever you are building the newest version of an image. But in general, that is supposed to actually be a version. So traditionally a number, or for the latest version of your image, you simply say latest. Now this is a convention right here. You're going to see all projects in Docker trying to follow this convention as much as possible. You might be wondering why some other images that we've been able to use have more simplified names like simply Redis or hello-world or busybox. Well, all those are community images. They are images that have been created by people in the community and kind of open source for very popular use. Anytime that you are creating an image of your own, you're always going to prefix it with your Docker ID. All right, so let's give this a shot and see how it works. So I'm going to flip back over to my terminal, and we are going to execute docker build -t, your Docker ID. So for me, it's Stephen Greider. For you, it's probably going to be something else, slash whatever you want the name of the project to be. So I'm going to use Redis. You can do Redis, you can do Redis server, really anything goes here. A colon, and I'll say specifically latest. And then don't forget, after all that stuff, we still have to put in that dot at the very end. Still need to specify that build context, which again is the source of all the files and folders that are going to be used to build your container out. One quick reminder, we're not really doing a lot with this build context yet, but we will use it for something later on in the course. All right, so once you got all that in there, we'll run that, and then the output down here says successfully built the image ID, but then it tagged it as this name. And so now we can start up a container out of this image by running docker run, and then using the name that we just provided of Stephen Greider, or whatever your tag is, /Redis. And then you do not have to actually specify the version on the end. You can simply leave it as your Docker ID /Redis. If you don't put on the version on the end, then the latest version of the container, or the latest version of the image will be used by default. So I'll run that, and sure enough, we get our Docker image running. All right. So one last quick kind of nitpick thing that I want to throw out here, just because you might see some documentation that looks a little bit confusing. Technically, the version number on the very end here, this is technically the tag. Now, the entire process of what we just did is known as tagging the image, and even the argument we used was -t right here. So we call this process tagging the image, but technically just the version on the end is the tag. Everything else on here is actually like the repository or the project name. So just a little bit of a nitpick. I just want you to be aware of that. All right, so that's pretty much it. Let's take a quick break, and we'll continue in the next section. Before we move on, there's just one last little quick thing that I want to show you around this entire image building process. Now, what I'm going to show you inside this section is not something that you're probably going to do very often or ever, really, but it's something that I thought you might find a little bit interesting and help you get a little bit of a better handle on the relationship between an image and a container. When we were going over the flow of actions that occurred while we were building the image, we spoke about how we take an image from the previous step, we create a container out of it, we do something with that container, and we then essentially create an image out of that running container, or that kind of very temporary container that was created. So at this point, you and I know very well that we use images to create containers, but based on everything that we've been talking about in this section, it sure seems like the opposite is kind of true as well. It seems like we can kind of take a container and generate an image out of it as well. And that actually is correct. You and I can manually create a container, run some commands inside of it, or change its file system, and then generate a usable image that we can then use at some point in the future. In other words, we can kind of very manually do the same thing that our Dockerfile does. We can create a container, run a command, like say apk add redis right here, and then generate an image out of that. I want to very quickly show you how that would look. But again, I really don't expect you to do this on your own personal project. I'm just showing you this as kind of something you might find interesting. So let's try to kind of emulate the Dockerfile that we just put together. We're going to create a new container manually out of the Alpine image. We're then going to install Redis on it. We're then going to set up a default command and generate a usable image that can be used in the future. Essentially everything that our Dockerfile just did. So at my terminal, I'm going to execute docker run, and we're going to start up a shell inside of here so that we can run a couple of commands inside of it. So I'm going to put on the IT flag. I'll put on Alpine as our image, and then the command that I want to execute inside there is sh to start up a shell. So then I get presented with a command prompt right here that is inside of that running container. Now, and so inside that container, I'm going to manually install Redis by running apk add --update Redis, like so. So we now have a running container where we have modified its file system. And the file system has now seen the installation of Redis. So we've got the running container. I'm now going to open up a second terminal window. And inside of here, I'm going to run a command using the Docker CLI that's going to essentially take a snapshot of that running container and assign a default command to it and generate an image out of the entire thing. So to do so, I'll say first docker ps to get the ID of that running container. And then we'll do docker commit. I'm going to add on a -c right here, which is going to allow us to specify the default command. So I'm going to say -c, and then I'll put in cmd, double quotes inside the square brace, redis-server. I'll close the double quote, I'll close the square brace, and I'll close the single quote. So notice how we have a single quote, and double quotes around it. And then after all that, I'll paste the ID of that running container. So I'm going to paste it in like so. And the output is the ID of a new image that we just customized for our own uses. Now you'll notice how this is a really long ID right here. One shortcut that I haven't quite mentioned so far, whenever you're making use of IDs or hashes in the Docker world, you don't have to copy the entire thing. You can just copy a segment of the start, and it's kind of assumed that this is going to be unique enough that Docker is going to take this and realize that, oh, you're probably talking about this very long ID right here. So I'm going to copy just an arbitrary number of leading characters here, and then we'll do a docker run that, and that's going to start up a new container out of the image that we just created. And inside that running container, we already have Redis installed, and the default starting command will be to run Redis server. So let's run that, and we'll very quickly see all the typical output that we see from a running Redis instance. All right, so like I said, we basically just very manually created a container, added a dependency to the container, set up the default command, and then generated an image out of all that. Again, you really don't want to use that practice in general. You don't use Docker commit in general. You really want to use the Dockerfile approach because it allows you to very easily rerun that series of steps again in the future. But again, I just thought you might find it interesting how, yes, there really is a very kind of fluid relationship between containers and images. All right, so let's take another quick pause right here and we'll move on to the next section. We've now successfully learned how to create a Docker image in order to run Redis on our machine locally. But there's still a lot to learn about creating an image and running Docker applications. So in this section, we're going to kick off a new project. The goal of this project is to create a tiny Node.js web application, wrap it inside of a Docker container, and then be able to access that web application from a browser running on your local machine. We're not going to worry about deploying this app right now. We're just focused on getting Node.js to work inside of a Docker container. Let me first begin by showing you a quick outline of some of the steps that we're going to go through. So the first thing we have to do is create an actual Node.js web application. Now, if you don't have any experience with Node.js and you're more of a Java person or Ruby or whatever it might be, that is totally fine. The code that we're going to write for the JavaScript side of things is totally optional. So you can either watch the video where we will put together the server, or you can entirely skip it and you can just download the single file or one or two files that you're going to need. So if you don't know anything about Node.js, no problem whatsoever. After we create the Node.js web app, we'll then author a Dockerfile. We're going to make a Dockerfile to create an image that is going to be used to run our web server inside of a container. So we're going to build the image from the Dockerfile. We will run the image as a container on our local machine, and then we will make sure that we are able to connect to that running web application inside the container from our browser. Now, last thing I want to mention here, and this might be something that makes you a little bit unhappy, but I'm just going to throw a disclaimer out here. We're going to do some things in this project a little bit wrong. So when we put together our Dockerfile, we're going to make a couple of mistakes. And we're doing this very much on purpose because these are going to be some mistakes that I really expect you to make when you start working on Docker on your own projects. So I want you to see these mistakes. I want you to see the error messages, and I want you to learn how to fix them. So just quick disclaimer, again, we're going to do things just a little bit wrong. Don't worry, I will be very clear when we come across an error, and I will say very, very clearly, hey, we did this on purpose, here's the mistake, and here's how to fix it. I know that sometimes in a tutorial, it's really frustrating when things are done incorrectly. I'm totally aware of that, so I'm going to make sure that these errors are as distinct and highlighted as possible. All right, so with that in mind, let's take a quick break. When we come back to the next section, we're going to start putting together this Node.js web application. So I'll see you in just a minute. In this section, we're going to start working on the Node.js web application. If you are not familiar with Node.js, or you don't know any JavaScript and you don't want to know any JavaScript, that is totally fine. You can pause the video right now, skip to the next section where I will have a text link for you to download the 2 files that you're going to need. So totally fine if you don't want to write any JavaScript at all. Otherwise, stick around and we'll get started on this tiny web application. So to get started, I'm going to first flip back over to my terminal. You'll notice that I'm still inside of that Redis image directory. I'm going to go up one directory, and then I'll make a new project folder, and we will call this, how about Simple Web? Because it's going to be a rather simple, straightforward web application. I'll then change into that directory, and then I'm going to again start up my code editor inside there. Now, a quick reminder, I was able to use the code command right here because I've set up Visual Studio Code to be executed from my command line. So if you don't have that set up, totally fine. All you really need to do right now is open up your code editor based on that simple web directory that we just created. Then inside of here, we're going to create first a file called package.json. Inside this file, we're going to put together a little bit of configuration to describe how our Node application is going to work exactly. I'm going to first begin by placing a set of curly braces. And then inside there, I'm going to place a key wrapped in double quotes. And the first section we're going to put together is going to list out all of the different dependencies that our application needs to run correctly. Notice how I'm wrapping the word dependencies inside of a set of double quotes. I've got a colon afterwards, and then I open up a curly brace object. Then inside that set of curly braces, I will put down another set of double quotes. And I'm going to say that in order for our application to work correctly, we need a copy of Express. I'll then put down a colon. And then for the version, I'm just going to put a star to say we can use any version of Express out there. We don't care. After that, I'm then going to put a comma on this line right here. And then I'll add in one more section. This is going to be a section that we will call scripts. And this will contain some of the different scripts that you can run to get our application up and running. I'm going to open up another set of curly braces, just like we did a second ago. I'll put a set of double quotes, and we're going to create a script called start. Anytime that someone runs the start script, we are going to execute node index.js, like so. This right here is going to be what ultimately starts up our server and gets it running. All right, so that's it inside of the package.json file. So we have specified a dependency and we've created a single script. I'm now going to make sure that I save the file, and then I'm going to close it and create a second file inside the same directory. And the second file I will call index.js. So inside of here, we're going to first begin by requiring in the express library that we just marked as a dependency. I'll then use the express library to create a new app, like so. And then we are going to set up one single route handler. We're going to say app.get. I'll pass in a string with a /. As a second argument, I'll pass in an arrow function that gets called with a request and response object, and open up a function body after placing a function arrow. Then inside of here, we'll do res.send, and we're going to send back a message of hi there. So now anytime someone visits the root route of our application, we are going to immediately send back a string that says simply hi there. And so ultimately, when we run our application, my expectation is that in the browser, we should be able to visit this running web application and see hi there appear on the screen. Now the last thing we have to do is set up our application to listen on a port. So down at the bottom of the file, I'll say app.listen, and I'll specify the port that we are going to be listening to as 8080. As a second argument, I'll pass in an arrow function like so. And then finally, after the app starts listening to this port correctly, we will print out a little message that says listening on port 8080, like so. And then I'm going to make sure that I save this file. All right, so that's pretty much it. We've got our package.json file that defines some configuration around our project, and we've got the index.js file that contains the actual server logic. So we're going to take a quick pause right here. When we come back to the next section, we're going to start talking about how we're going to put together our Dockerfile. So quick break, and I'll see you in just a minute. In the last section, we put together the core of the Node.js web application. If you didn't follow along in the last section and you just copy pasted the code, just make sure that you've got your index.js file and a package.json file. You'll also want to make sure that you've got your terminal open inside of your project directory. And so if I list out my current files and folders, I should see the index.js and package.json files. Okay, so we've got some source code here, and now we need to figure out how we can wrap this all up inside of a Docker container. I want to first begin by telling you a little bit about Node.js and how we're going to start up this application. So just in case you've never made use of Node before, two commands that you need to be aware of to install dependencies and start up this application. Anytime that we want to start up a Node app, we have to first install a set of dependencies. And we can install all of our dependencies by running a command npm install inside of our project directory. This starts up a little program called npm, which is somewhat colloquially known as the Node Package Manager. This is going to run that program and install a couple of dependencies for us, and of course it assumes that npm is installed on our local machine, or inside the container, as the case may be. The other thing to be aware of is that we're going to have to eventually start our server up, and to do so, we're going to run the command npm start at the terminal as well. And again, this also kind of assumes that npm is already installed. All right, so with all this in mind, let's now start thinking about the Docker file that we have to put together. Now, the series of operations that we are going to put into the Docker file is going to end up looking very similar to what we did in the last application. So in this somewhat complicated diagram, our template that we're kind of following here for our Docker file is to specify a base image, run some command to install some dependencies, which definitely sounds like something we have to do, and then specify the command to run on startup, which, as we just discussed, is that npm start thing. Now, when we were working on the Redis image, we said from Alpine to specify the base image, we ran apk add redis to install the dependency, and then we set up the default command as Redis server. And so it really seems like we have some very direct parallels this time around. I think that for the Node application, we could probably do a Docker file that specifies Alpine as our base image. We can then run npm install to install all of our dependencies, and then we can set up the default command of npm start to run the server when the container first comes online. So we're going to take this type of approach right here by creating a Docker file and then essentially putting almost exactly these instructions inside of it. Now, quick disclaimer here. Remember, I had said we're going to do a few things here slightly wrong, just so you can see some very common error messages that you are just about guaranteed to see on your own personal projects. So maybe in this discussion or the series of steps that I just described, there might be something in here that doesn't quite line up with what's reality or what we really have to do, okay? All right, so let's get started. I'm going to begin by making sure I've got my code editor open based on that simple web directory. And inside of here, I'm going to make a new Docker file. Remember, it's Docker with a capital D, and there is no file extension on there. Then inside of here, we're going to first specify our base image. And just to be really complete, I'm going to add in some comments for these steps just to remind you what we're doing every step along the way. So I'll say specify a base image. And you know what? Let's use that Alpine image again. It really seemed like it worked out last time for us. Next up, we're going to install some dependencies. To do so, we will run the command npm install. Like I just said, the npm install command is how we install dependencies on a Node.js project. And then finally, we will set up a default command, which we can do by writing out cmd. And then we put down a set of square brackets. And then in a set of double quotes, we separately list out all the parts of the command that we want to run when the container is first created. And so to start up our server, we are probably going to want npm start, like so. Notice that I've got a comma between those two strings. All right, I think this looks pretty good. It definitely looks very similar to what we did for Redis. So let's now flip back over to our terminal and see what happens when we try to build this image. So I'm going to list out my files and folders and verify that I now see the Docker file inside of here. And then remember, to build an image, we can run docker build, and then we put the dot in there to specify the build context of the current directory. So I'll run that, and then we very quickly see npm not found. All right, so first problem of a couple that we're going to see. So let's take a quick pause right here. We're going to start to investigate why we are seeing this error and fix it up. So quick break, and I'll see you in just a minute. In the last section, we took a first stab at our Docker file to build out this Node.js project. But we very quickly saw that during the run npm install step, we got an error message that said npm not found. We're seeing this error message because during step number 2 right here, where we try to execute the command npm install inside of a temporary container, there is no copy of npm available. We're seeing this because we are using Alpine as our base image. Remember, we had said that we select our base image based upon the collection of default programs that we need to successfully build our image. By default, Alpine is a very small image. It's only about 5 megabytes large. And so it has a rather limited set of default programs included inside of it. In fact, I kind of like this diagram right here. What programs are included in the Alpine image? Well, this is supposed to be a tumbleweed of sorts. Not much. So there's not a whole lot of stuff going on by default inside the Alpine image. You get a couple of very default Linux or Unix programs. You get that package manager that we used just a little bit ago, but that's pretty much it. You don't get a lot of other stuff for free. So when you are using the Alpine image and you expect to run some fancy web application depending upon Node.js or depending upon Ruby or Java, chances are you are going to have to do some additional fixes or some additional setup to get this thing working. Now, to solve this issue, to solve the issue of npm not being available inside of our base image, we have 2 options. The first option is to find a different base image. We can try to find a base image that already has Node and npm pre-installed inside of it. Alternatively, we can continue using the Alpine image and run an additional command, like right here, to attempt to install Node.js and npm inside of our image. So 2 approaches. We can either essentially use someone else's work, or we can try to build up our own image from scratch. In our case, we're going to try using someone else's image. We're going to find an image that has already been configured to have npm pre-installed inside of it. So to get started, I'm going to flip back over to my terminal, and we're going to navigate to Docker Hub, which you'll recall is a repository of public images that we can easily pull into our build process. So I'm going to open up a new tab and navigate to Hub, .docker.com. And then on the top bar, I'm going to find the Explore button. You'll see a listing of very popular images immediately appear. And so, of course, right there is Alpine. We're going to scroll down a little bit. And a few options down, you'll see Node listed right here. If you don't see Node listed on here, you can always do a search up here at the top left-hand side. And we're essentially just looking for the repository called Node, and it should have a little subdescription of official. So we can click on this. We'll get a short description right here. Now, the description in this case is not super helpful. It says, oh yeah, Node.js, here's what it is, but well, what are we really downloading? Like, what is this repository? This repository is a Docker image that has Node pre-installed on it. So if we want to, we can attempt to build our image based upon this Node one. And this Node image already has Node pre-installed, already has npm pre-installed, and so we don't have to worry about getting more errors like this, where npm is not found. Now, before we just go and use Node willy-nilly, I want to show you a little bit more inside this description. So you'll see this full description panel right here. And then first section in here is supported tags and respective Dockerfile links. So this is a listing of all the different versions of this image that is available. You can get different versions of Node.js encapsulated in each of these different tags. So for example, if I have an application that requires Node version 6.14, I can find the tagged version 6.14 right here. And then inside of my Dockerfile, when I specify my base image, I can say Node, and I can specify the version of it specifically by adding on 6.14. So this will give me an image that contains a pre-installed version of Node.js, specifically version 6.14 of Node.js. Now in our case, we don't want version 6.14. Instead, I want you to scroll around just a little bit and you'll eventually see one tag in here called Alpine. You might have to do a Command F search for Alpine, and you'll see that, well, yeah, there's a lot of examples on it on here. So here's Alpine right here. I want you to remember this is a tag, so this is not the name of the repository. So when you see Alpine right here, it doesn't mean that we're supposed to use like Alpine like we were just before. The first word right here is the name of the repository. You place a colon, and then you put down a tag name. And so in this case, when you see Alpine right here, it means that we can optionally select Node:\Alpine. So now you might be curious, why would we do this? Like, what is the purpose of Alpine being tied onto Node? Well, Alpine is a term in the Docker world for an image that is as small and compact as possible. Many popular repositories are going to offer Alpine versions of their image. And an Alpine version of Node in particular means that you're not going to get a bunch of additional pre-installed programs. So the default Node installation might include extra programs like, say, Git or a package manager or, I don't know, some fancy text editing tools inside that image. When you get the Alpine version of an image, it means you're getting the absolute most stripped down version of that image possible. So it's going to essentially have Node.js and pretty much nothing else. It will have some very basic programs like, say, the ping command. Maybe, you have to look at the actual image to figure that out, but it might have the ping command. You'll have, say, cat, maybe a simple text editor, ls, simple programs like that. But in general, you're getting a very stripped down version of that image. So for us, the Alpine version works just fine because essentially all you and I need is Node and npm. And npm is included in this Node image right here, and we need absolutely nothing else. So we are totally fine using the Alpine version of the Node image. All right, so with all that in mind, now that we've made the change to the from right here, we now have specified a base image that hopefully is going to include npm inside of it. And I can tell you it definitely is. This is going to have npm pre-installed. We're definitely good to go. So let's now try to rebuild our image with this change and see if that error message goes away. First things first, do make sure that you save the Docker file. And then once you save it, we'll flip back over to the terminal and do a docker build dot again. All right, so now you can see that we're downloading the new Node Alpine image. We then get down to step number 2 right here, where we run npm install. But very shortly after that, we get a series of error messages, and the first of which says, no such file or directory, package.json. So the package.json is a file that exists inside of our current working directory. But it looks like the container is complaining that, hey, I don't have this file available, like, where's the package.json file? I need this to know which dependencies I need to install. So let's take a quick pause right here, and we're going to start to investigate why we're seeing this error message. In the last section, we made a little change to our Dockerfile and then tried rebuilding the image. The good news is that npm is now clearly being included inside of our container, and so it's attempting to install dependencies. However, npm itself very quickly threw out an error message right here, complaining that there is no file called package.json available. Now, just in case you weren't around or you kind of skipped over the section where we put together the package.json file together, that is a file inside of our project directory right here. Its purpose is to list out all the different dependencies that are required to successfully run our project. So when we run npm install, npm is going to try to find this file. It's going to find all the dependencies that are listed, and then it's going to try to install each of those. So clearly the issue here is that npm is not finding that file. So let's talk about why it is. All right, so quick diagram. We've looked at this one before. We've got our container on the right-hand side. We've got the steps out of our Dockerfile, and then down here is a little representation of the node Alpine image that we're making use of. So let's imagine what is going on inside of our image building process right now. First off, we specify node Alpine. That downloads the Alpine image, or excuse me, the node image to be precise. And then the next step starts up and it says, okay, I'm going to go back to the previous step and get the image from there and then create a temporary container out of it. So as soon as run npm install starts to boot up, we can imagine that we take this file system snapshot right here and we kind of put it into this very temporary container. And then we execute npm install. Now, got a quick question for you. Do you see anywhere inside of this file system right here, do you see a package.json file? Well, the answer is no. There is no package.json file available inside of the container. The only files and folders that are available inside the container is exactly whatever came out of the file system snapshot from the node image. Remember, we are only working with a segment of our hard drive inside this container. There's this entire other rest of the hard drive kind of like not connected inside this container. And somewhere inside the rest of the hard drive is where our package.json file is. And that is not at all being communicated into the container. And so we do successfully run npm install, but there just plain is no package.json file available. So the takeaway here is that when you are building an image, none of the files inside of your project directory right here are available inside the container by default. They are all 100% sectioned off, completely segmented out. They are not at all available, and you cannot assume that any of these files are available unless you specifically allow it inside of your Docker file. So as you might guess, that's exactly what we're going to do. We're going to add in one line of configuration to our Docker file to make sure that both our index.js file and package.json file are available inside the container when we try to run the npm install command. Let's take a quick pause right here, and then we're going to add in that additional instruction in the next section. In the last section, we saw that the npm install command failed to run because the package.json file was not found, and we spoke about why that was. In this section, we're going to figure out how we can make sure that the package.json file is available before npm install is executed inside of the container. To do so, we're going to add one little instruction to our Docker file. This is going to be an instruction that we've not used before. It's the copy instruction. And as you might guess, the copy instruction is used to move files and folders from our local file system on your machine to the file system inside of that temporary container that is created during the build process. The overall syntax for this is copy, then a path to the folder on your local file system, and then the path that you want to copy that stuff to inside the container. Right now, I'm showing these commands with a /, which means the current working directory. Now, one little technicality here, the path from our folder, the first argument right here, is relative to the build context. And you'll recall that I had said that the build context is the dot right here when we execute docker build at the terminal. So build right here means simple web directory or the current working directory. So we have set the current build context to be simple web. So then inside the copy command right here, when I say /, that means the build context, which is simple web. I know that's a little bit confusing. It's essentially kind of like 2 layers of indirection. Again, we're going to see a better example of why we would alter this build context stuff in the future when we start working on some more complicated projects. For right now, all we really need to know is that if we add this right here to our Docker file, we're going to copy everything from our current working directory into the container. And that's pretty much it. So let's flip over to our Docker file, and we're going to add in this instruction and then try to rebuild our image. Now we definitely want to make sure that the package.json file is available before we run npm install. So I'm going to add in the new instruction right above that. So I'll say copy // Again, everything from the current working directory of simple web to the current working directory inside the container. All right, so I'm going to save this, and then we're going to try to run the docker build command again over at our terminal. So I'm going to flip back over, and I'll do docker build dot. We'll run that. Now, between the last section and this one, I removed my Alpine image, or the node Alpine image, so I had to re-download it. But after that, we should see the copy step. There it is right there. We'll then see npm install. Now, you will notice a couple of little warnings. The warnings are totally fine. If you see a notice and then 3 warnings in a row, that's totally fine, no issue. So we've now successfully installed all of our npm dependencies. And then if we keep on scrolling down, we'll eventually see at the bottom that we have correctly generated this new image. And this is the ID of the new image. Now remember, it's not really nice to work with IDs all the time. Let's try running the docker build command again, but this time we're going to tag the image. So I'll say docker build -t, then my Docker ID, and then the name of this project, which we are calling simple web. And then I'm going to make sure that I pass in the build context on the very end. You'll notice I did not put on the :latest to the tag right there. It's because, remember, the :latest tag is automatically appended if you don't specify it in here. Now, one thing I just want to remind you about, please don't forget the dot on the very end. And once you've got that all on there, we'll hit enter to rebuild it. And now we have tagged that newly built image as your Docker ID /simple web. So now last thing we're going to do is try to start out that image and get the node server running. So I'll do a docker run Stephen Grider /simple web. All right, so I very quickly see that the node index.js command was issued through the npm start command. I then see that the server is correctly listening on port 8080. So I think that we're ready to open up a web browser and test this thing out. So I'm going to flip on over to my browser. And to visit that running application, we should be able to go to localhost :8080. But once I do, I get a nasty little error message that says this site can't be reached. Well, we definitely got our image built and we are running a container out of it, but we still are not able to actually visit this port or see the web application running. So let's take a quick pause right here and we'll continue in the next section and figure out what is going wrong. In the last section, we were able to successfully build our image and then start up our container based on it. We saw the message listening on port 8080, but when we actually tried to visit localhost 8080 inside the browser, we got a pretty nasty error message. So let's figure out what went wrong and how to fix it. All right, so here's a diagram of what's happening right now. Our browser is making a request to localhost 8080, which is essentially a reference to your current machine on port 8080. By default, no traffic that is coming into your computer or into your localhost network is routed into the container. So the container essentially has its own isolated set of ports that can receive traffic. But by default, no incoming traffic to your computer is going to be directed into the container. In order to make sure that any request from either your computer or some outside computer will be redirected into the container, we have to set up an explicit port mapping. A port mapping essentially says anytime that someone makes a request to a given port on your local network, take that request and automatically forward it to some port inside the container. So in other words, if anyone makes a request to localhost 8080, take that request, automatically forward it into the container on port 8080, where the node application can then receive it and process the request and eventually respond to it. Now, one thing that I want to make sure is really clear right now from the get-go, this is only talking about incoming requests. Your Docker container can, by default, make requests on its own behalf to the outside world. We've already seen that in action anytime that you've been installing a dependency. When we ran npm install during the Docker build process just a moment ago, npm reaches to the outside world. It reaches out across the internet. And so there's no limitation by default on your container's ability to reach out. It's strictly a limitation on the ability for incoming traffic to get into the container. So in order to set up this mapping, in order to kind of forward this traffic to a specific port inside the container, we're going to make a slight adjustment to the way in which we start the container up, or specifically the Docker run command. So this is not a change that we're going to make to the Dockerfile. We do not set up port forwarding inside the Dockerfile. The port forwarding stuff is strictly a runtime constraint. In other words, it's something that we only change when we run a container or start a container up. So here's what we're going to do. To set up Docker run with port mapping, we're going to add on a -p flag. The syntax overall is Docker run, then -p. Then we're going to specify that any incoming traffic on our local network to this port right here should be automatically forwarded on to this port inside the container right here. And notice how there's a separation between these two ports, or these two numbers, of a colon. And then as usual, after that, we're going to specify either the image ID or the image name, which is what we are now using. So let's flip over to our terminal and we're going to give this a quick shot. I'm going to first stop the running container by pressing Control-C, and then I'm going to start the container back up, but this time I'm going to set up some port mapping. So I'll say anytime a request comes in to 8080 on my local machine, redirect it to port 8080 inside the container. And then I'll make sure that I still specify the image that I want to use for this container as my Docker ID. You'll put whatever yours is right there. Simple web. And I'm going to get that on to just one line, like so. Okay, so let's start this. Now from the outside, it looks like everything is still identical to how it was before, but if you flip on over to your browser, open up a new tab again, and go to localhost 8080, you'll very quickly see the text "Hi there" appear on the screen. This is the response that we would expect to see from the running node application. So that means that we are now correctly forwarding incoming requests into the container. The node application is processing the request and then sending a response back out. So that's pretty much it. That is port mapping in a nutshell. Now very quickly, one last little thing that I want to show you, because this will be done very frequently on real projects. The port from the source machine or the source network that we are mapping from to the port that we are mapping to inside the container do not have to be identical. So we could very easily say, hey, anytime that a request comes into localhost 5000, redirect that request to 8080 inside the container. And like I said, this is actually something that we're going to do quite frequently in production applications. So now this is essentially saying, okay, browser is making request to 5000, redirect request to 8080 inside the container. Again, these two ports do not have to be identical. So let's try doing that again with the Docker run command. I'm going to stop the thing by pressing Control-C, and then we'll do Docker run -p, and I'll say that I want to map port 5000 on my local network to 8080 inside the container. And then I'll do Stephen Greider, simple web. Okay, looks like everything started up successfully. Now if I go back over to my browser and I try to refresh localhost :8080, I'll very quickly see an error message. But if I instead go to localhost 5000, well, there's the node server. It is now taking traffic or incoming requests to localhost 5000 and redirecting them to 8080 inside the container. Now, last thing you might be kind of curious about, this is kind of an obvious, but I'm going to say simultaneously silly question. Can we change the port inside the container? Well, yes, of course. We can change this to be, 6000, 7000, whatever you want it to be. Just if you change the port inside the container, you need to make sure that your actual web server application, so inside my index.js file, we specified that our node application should listen on port 8080. So if you're going to change the target port inside the container, well, of course, you got to make sure that you change the port that your application is listening to as well. You would have to change this to 6,000 or 7,000 or whatever it might be. Okay, so that's it. That is port mapping in a nutshell. The one big thing to remember is that we have to specify it at runtime, not inside of the Dockerfile. So we've got one more step towards success. We are actually able to visit our running application inside the browser. So like I said, we were going to run into a handful of little errors along the way. We saw a case in which we were not copying over the package.json file. We saw using a bad base image, and we also saw a lack of port forwarding. Again, these are all little things that I kind of expect that you'll see as soon as you start using Docker on your own personal project. Now, even though our application is successfully running, there is one last little thing that I want to point out. So we're going to go over one last little fix in the next section. So quick break, and I'll see you in just a minute. We're now successfully able to visit our running web application inside the browser, but there's one last little thing that I want to point out. I'm going to start my container up using the image that we've already built, but this time I'm going to start up a shell inside the container so that we can do a little bit of debugging inside there. Remember that we can start up a shell inside of most Alpine-based containers by running docker run -it, and I'll put down my container name of Stephen Grider simple web, and then I will override the default startup command with sh. Remember, this is a reference to the shell program. It will start up a shell that we can type commands into inside the container. Now you'll notice that I did not specify a port mapping here. It's because we are not going to actually start up the server. I just want to attempt to look at the files and folders inside the container. So I'll run that, and then we'll get a command prompt based inside of the root directory of the container. Now inside of here, I'm going to print out all the available files and folders with ls. So inside of here, you'll notice that when we did that copy operation, we copied into the root directory or the root folder of the container. And so in this root directory, we can see the Dockerfile, a packagelock.json file, which is automatically generated by npm, package.json, index.js, and all of our installed dependencies were placed into this node modules folder. And again, these were all placed into the root directory of this container. Now, this is definitely not the best practice. And the reason for that is that if we happen to have any files or folders that conflict with the default folder system, like if we have a folder called var or root or run or lib, super likely for us to have a folder called lib inside of our project, we might accidentally overwrite some existing files or folders inside the container, which is definitely not ideal. So we're going to make a little change to our Docker file. And rather than copying everything directly into the root project directory, we're actually going to copy everything into kind of a nested directory instead. Now, rather than just changing the copy command inside of our Docker file and saying, oh yeah, copy it into like some application folder or something like that, there's actually an instruction that we can use inside the Docker file that is specifically meant to address this whole issue right here of accidentally overwriting files or folders by copying into a root directory. So let's take a look at what the instruction is. So we can add the work_dir or work directory instruction into the Docker file and then pass a reference to a folder to it. Then any following commands or any following instructions that we add to our Docker file will be executed relative to this folder. So in other words, if we add the work_dir and then a folder above the copy instruction right here, it will make sure that we only execute, or excuse me, it'll make sure that when we actually do the copy instruction, it won't copy it into the work directory, excuse me, the root directory, it'll copy it into the directory that we have specified as the working directory instead. So let's try doing that right now. I'm going to add in an instruction of work_dir, and then we're going to use a folder of /user/app. So I'll say /user/app. If this folder does not exist inside the container, it will be automatically created for us. Now you might be curious as to why I'm using user/app. Well, to be honest, in the Node.js world, it doesn't make a tremendous difference where you put your application into in a Linux-based operating system. There definitely are places you don't want to put it, but at the end of the day, the user folder is a safe place to put your application. It's specified as the location for all of user home directories. Essentially, it's an okay place for us to put our application. Now, as I say that, there's definitely a lot of Linux diehards out there who would probably disagree with me, and they might say, oh no, you should put this into var, or you should put it into the home directory instead. So there is some disagreement out there on where the best place is for your application, but I can just about guarantee you that if you put it into user/app, you're probably going to be okay. Okay, so now we've added in the workdir instruction. I'm now going to save the Docker file, and then we'll flip back over to our terminal. I'll exit the running container by typing in exit, and then we're going to make sure that we first rebuild our container, and then we will try to relaunch it. So I'll do a rebuild with docker build dot. Oh, let's not forget to tag it. So docker build -t your docker ID /simple web, and then a dot. There we go. So we're going to rebuild it. Now, one thing that you'll notice is really interesting, because we made a change to an instruction above the copy and npm install, everything after that instruction has to rerun from scratch. So we cannot use any cached versions. In other words, the npm install command has to run again and reinstall all of our dependencies, because we cannot use the cached version of that step. So we got our output here. Let's try starting up our container again. I'll first start it up in normal mode and try to visit it inside my browser. So we'll do a docker run -p to set up a port mapping, and we'll map 8080 to 8080. And then the container that I want to run is Steven Grider /simple web. So we'll run that, and then I'll go back over to my browser. I'll try to visit localhost 8080, and yep, it looks like we're good to go. I can refresh the page. And if we also try to start up a shell inside the container, we'll see that all of our project directories, or excuse me, all of our project files are no longer in the root directory. To do so, we can either rerun the docker run command with the IT and sh attached to it, or we can use that docker exec command. You'll recall we can use docker exec to start up a second process inside of a running container. Let's try doing it that way just for a little bit of variety. So I will open up a second terminal window. I'll get the ID of that running container by using docker ps. So here's the ID right here. And then we can attach to that container and start up a shell inside of it by using docker exec -it, the ID of the container, and then the program that we want to run inside of it, which in this case is shell. Don't forget the IT right here is to attach standard in and a nice looking terminal to the shell that starts up. So I'll run that, and you'll notice that we enter directly into the user/app folder because we had set up that working directory previously. That workdir instruction right here not only affects commands that are issued later on inside of our Docker file, it also affects commands that are executed inside the container later on through the docker exec command. So if I now do an ls right here, I'll see all of my project files and folders nicely isolated inside of this single file. And I can change back to my root directory by doing cd /, print out all the files and folders there with ls, and I'll see that I do not have any possible conflicts going on. We have nicely spaced our application, or kind of isolated our application into this folder right here. All right, so that's pretty much it. Looking pretty good. Now, believe it or not, there is one last little thing that I want to look at. So let's do one more quick break, and we'll come back in the next section and do one quick last little thing. So I'll see you in just a minute. There's one last little interesting thing that I want to show you about our current build process and the container that we're running out of it. I'm going to start up my container very quickly with docker run. We'll do the port mapping again with 8080 8080, and I'll do Steven Grider /simple web. Okay, so we're running on port 8080. Now I'm going to again visit the application inside the browser. I'll refresh the page. Yep, everything's working as we expect. Now let's try making a change to the source code of our index.js file. I'm going to open up the index.js file right here. This is the route handler right here that is executed anytime someone visits the root route on our running server. And so as you can see, we are sending back a string of simply hi there. Let's try making a change to this string. and then refreshing the page and seeing what happens. So I'm going to change from hi there to bye there. I know I'm not very original. I'm going to save this file. It definitely saved. I'm going to go to File Save, 100% saved, no two ways about it. And then I'm going to go back over to the browser and I'll refresh the page. And when I do so, you'll notice that we still see hi there appear on the screen. So what's going on? Well, remember, anytime that we create our image or create the container, we're taking a snapshot of the file system. So we took a snapshot of index.js after it got copied over. And we are running our application based on that old version of index.js. When we modify the index.js file inside of our current working directory right here, that change is not going to be automatically reflected inside of the container. If we want it to update the file inside the container, we're going to have to do some additional fancy configuration. We're not going to go through that configuration just yet. That's going to be something that we're going to address on the next application. But just so you're aware, yeah, changes we make here, not reflected inside the container. So what would we have to do to get our container to get this new file, or to get this new change right here? Well, we would have to completely rebuild the container. We would have to rerun the docker build command and attempt to build it again, which is going to copy over the newly changed files, then run npm install, and then start our server up. Let's go through that process right now because there's one more little thing that I want to show you along those lines. Okay, so I'm going to stop my running server, and then we'll do a docker build. We're going to tag it, and then I'll make sure that I do the dot to specify the build context. So I'm going to run that, and oh, this is kind of interesting. I want you to notice something here. During step 3, we are copying over all of our project files and folders, every last one of them. We just made a change to the index.js file, and Docker has detected that we changed one of the files that was copied over during that step. Because we made a change to this step right here, step number 3, and every step after it has to be executed again. In other words, when we rebuild our container, we have to reinstall all of our dependencies, even though we very clearly did not make a single change to any of the dependencies inside of our project. And so I'm going to argue that that's probably not ideal. If we don't make a change to a dependency inside of the project, we probably don't want to rerun npm install. All we did was change one of the source code files of our project. And again, that has nothing to do with our dependencies. So I think that would be really neat if we could figure out a way to make sure that just by changing one of our source code files, we do not have to rerun npm install and install all of our dependencies again. Because even though this is only taking a handful of seconds right now, well, it's only because we have one single dependency. If you're working on a real application or a real project, it might take several minutes to rerun the npm install command. And I would not want you to have to reinstall all those dependencies every time that you make a change to the source code of your project. So let's come back to the next section, and we're going to figure out a better way to handle copying over our project files and folders into the container. So quick break, and I'll see you in just a minute. In the last section, we saw that making a change to our index.js file and then rebuilding the image caused the copy step to be completely invalidated. We had to rerun copy and every step after it, which means we had to sit through and wait for all of our dependencies to be installed through run npm install. So in this section, we're going to try to figure out a way to avoid having to completely reinstall all dependencies just because we made a little change to one of the source code files inside of our project. So here's what we'll do. We're going to take our current build process inside of the Dockerfile, and we're going to split the copy operation out into 2 different steps. The only thing that npm install right here requires in order to run successfully is the package.json file. That's all we care about. We don't care about the index.js file or any other file inside of here. So during this initial copy step, I'm going to say the only thing that I want to copy is the package.json file. So I just changed the instruction right here. It now says look in the current working directory, or look in the directory specified by the build context argument of Docker build, and find the package.json file. And then copy that into the current working directory of the container. We'll then run npm install. And then after we install all those dependencies, we'll copy over everything else. And so we'll do a copy .. like so. So think about what is going to happen now as you start to work on your project. You can make as many changes as you want to the index.js file, and it will not invalidate the cache for either of these steps right here. The only time that npm install is going to be executed again is if we make a change to that step or any step above it. And so in other words, the really only effect this is going to have is if we make a change to the package.json file. That's really the only situation in which npm install will normally be executed again during the build process. All right, so let's try building this again and then starting the container up and just making sure that everything still works. All right, so I'm going to flip back over. I'll do a docker build -t, Stephen Greider, again, your Docker ID, not mine, simple web, and then we'll specify the build context with that simple dot. So I'm going to rerun this. Now we have made a change to the Dockerfile, so we are going to see some steps rerun, and then we eventually get our successfully tagged and built image. Now before trying to run it, I want you to run the same command a second time. So same thing, no changes whatsoever. So that time it went extremely quickly because we were able to use the cached version of every single step. So now let's imagine that we are doing some normal changes to our application, and a normal change would probably be a change to the index.js file. So maybe we decide that we don't want to say bye there anymore. Maybe instead we want to send back, how are you doing? So we've now made a change to the index.js file, and we definitely need to rebuild our image because we do not have any support for kind of hot reloading of the index.js file or a project file into the container. So we have to rebuild the image. So I'll go back over. I'm going to rerun the same command for a third time. And we saw that it executed very quickly because the only change that we made to any step along the way was step number 5. We copied over the entire contents of that directory. Docker detected that we made a change to one of those files, and so it reran that step and every step after it. But we did not have to rerun the npm install step and reinstall those modules, which would have taken, in our application, not very long, but in a real application, it could take several minutes to run. All right, so the real lesson to learn here is that yes, it does make a difference, the order in which you put down all these instructions into your Docker file. And wherever possible, it is kind of nice to segment out the copy operations to make sure that you are only copying the bare minimum for each successive step. All right, so that's pretty much it for this application. Now, I hope that it was not terribly annoying for me to show you kind of like some of the wrong way of doing things and then correct them along the way. I hope that it was kind of nice to see the error messages appear and see the changes that we made. Of course, we could have put the right Docker file together from the get-go, but I don't know, you probably may have not learned quite as much as seeing the errors occur and then fixing them in as they occurred. Now, I think this application has turned out pretty well, but it's definitely a very, very basic operation. So let's take a quick break right now. We're going to come back to the next section and we'll start working on a much more advanced Docker project. So I'll see you in just a minute.